Welcome to Sarfatti Science Seminar's Cortona 2023 event. It's May 24th, and today's speakers are Dr. Maurice Passman on the wave dynamics of post-quantum mechanics, Larry Lemke on do UFOs contain exotic material, and Arik Shimanski on the solution to David Chalmer's hard problem. I'm your moderator, Tim Ventura, and we'll begin with the discussion of wave dynamics of post-quantum mechanics by Maurice Passman.
Well, thank you everybody for attending. And first I'd like to thank Jack and Gaetano for inviting me to speak today. I'm going to keep this presentation at a fairly non-technical level. The main reason for this is that often the narrative behind much of the mathematics that's been undertaken is lost to the average reader. I want to go into some of the background of the work that myself and Jack have undertaken to give you a flavour of the individual parts that make up the whole picture. So I'm going to mention a couple of papers and some up-and-coming publications on the horizon, and the full mathematical details can be seen in these papers, and the maths in this presentation will be referred to those. If you want any further details, please feel free to email me, contact me, and I'd be happy to give you some further information. First, some personal background. Jack's you probably know of already, but mine probably not. My background is in theoretical quantum mechanics. My doctorate was on forbidden transitions in quantum mechanics. So essentially looking at real life data that supposedly broke the laws of physics and trying to encompass what we were seeing, mostly in luminescent spectra, into a derived form of quantum mechanics. So attempting really to bring into the quantum mechanical theory fold observations that seemingly disobeyed quantum theory. From there, I moved on to working for the UK MOD, designing real life simulation models, notably predictive combat models, simulation models that concentrated on the soft aspects of conflict, such as social and political operations, essentially operations other than war, peacekeeping, this kind of thing. The latter part of my term at the MOD, which was in a unit called the Centre for Defence Analysis, at the end of my term, I moved on to visiting the Santa Fe Institute. So a lot of my background is in quantum mechanics, but also modeling from what you could call broadly complexity theory. So that's the kind of flavor that I bring to the current work, quantum mechanics side of it, plus the complexity mathematics, fractal mathematics, in a real hardcore sense. I then moved on to working in the finance industry, mostly in regulatory capital, and then subsequently worked at the Bank of England, which is, if you don't know, the UK's governmental agency that ensures the health and security of the UK economic and financial system. And I was one of the members of their policy unit that designed policy mostly for the insurance industry. Where myself and Jack came into it, my collaboration with Jack began around about 2018 after some correspondence I had with him, and we eventually met in London, where I'm currently based. The project that we set up was called the Red Door Project, the name after the door of the color of the door that of the accommodation that Jack lived in. We decided at that time to focus on two different general areas. Jack was going to concentrate mainly on his gravitational work, which he's spoken about in the past, and me working on the further developments of post-quantum mechanics, his post-quantum mechanics. In particular, the focus was going to be on consciousness, and also a certain part of the work was going to be looking at quantum computation. The results of the collaboration led to publication of two main papers. These outlined the fundamental characteristics of post-quantum mechanics. These also laid open a foundation for the closed doors work that we were then proposing to undertake, and I'll go into a little bit more detail of that. But essentially, these are the two papers that you should reference to with regards to the greater detail of the mathematics. They give, in a sense, a mathematical framework for the talk that I'm going to give today. So if you're interested in that, please go to those. The last thing is that one of the works that I'm undertaking now is a paper on gravitation with Jack that will hopefully be submitted to a peer-reviewed journal, hopefully Nature, at the end of June, beginning of July. That's the plan. So our fundamental ideas are based on essentially two questions. How is it that the effect of chance is computable? In other words, that random causes can have law-like effects. And secondly, how can randomness arise if all events are reducible to deterministic laws of nature? So again, I'm giving you a kind of flavor of narrative of what's going on behind the hardcore quantum physics. And we've got a number of two equations here. Let's have a look at the first one. So what we have here is the first one, A plus B goes to C. That's a chemical equation. And what we see in most chemical equations are what we expect. In other words, what we typically expect to occur. So the association of this kind of typicality is with Boltzmann-Gibbs ensemble. So the underlying thermodynamic mathematics is Boltzmann-Gibbs. In this particular equation, it's a reversible reaction. So what we have is we have this K, which is defined as an equilibrium constant, and the constant is defined by the concentration of the substances on the right-hand side divided by the concentration of the substances on the left-hand side. So the little square brackets are referring to concentration. Now, the stress is on the word constant. It's an equilibrium constant. So although we've got a dynamic system, that if I add more of A, the system goes to the right, producing more C. If I take C away, the system goes to the left, producing more A and B. The system is actually defined by, the dynamics is defined by this constant. It's a constant. So we have to affect the forwards and backwards arrow to move the system out of equilibrium. In other words, this system is in equilibrium, even though it's dynamic, but the core concept that we have to consider is how do we change that reversible arrow? So the work in a chemical sense first was investigated by Prigogine. So if you want to have a look at the chemical aspects of this, as opposed to the theoretical physics of it, he's a good place to start. So this is something fundamental that we have to understand, is that we have a dynamic system. It's in equilibrium. It's in equilibrium, and what we mean by that is that we are going to see something which is typically expected. This is based on classical standard Boltzmann-Gibbs thermodynamics. But if we want to change that system in a radical way, in other words, move it out from equilibrium, what we have to do is affect that double-headed arrow. So the moot question is, how do we actually undertake that? The second equation, dA by dt equals minus kb. This is called a Lanchester equation. And the equation was designed in about 1914 by this fellow called Lanchester. And it's designed to model combat losses. So the losses of A, so A is one side, depends upon the numbers of B and some constant. And the minus there is telling you that in this conflict, A is going to lose members. It's going to lose numbers. The interesting thing about this equation is that in reality, the K, the constant, changes with time. In actual fact, if I remember rightly, the only instance where we have this constant being a constant for a significant amount of time is in the combat in Okinawa in 1945. So again, what we have is a dynamic system that's supposedly in equilibrium, but in reality, we don't see that. So again, we have to think about this notion that what we have is that we have a series of systems that we're observing that supposedly work in terms of equilibrium mathematics, but there's something strange going on around the outside where we're not seeing this kind of behavior. Quantum equilibrium is associated with Born's law, which is something that we're going to talk about at a greater length in a moment. So if you look at real systems, real aggregate systems, such as financial markets, things like earthquakes, combat, political systems, what you realize is that they are influenced by external effects. So in other words, you could have a series of mathematics that describes a stock market movement, and you could attempt to model this in a particular way by looking at the agents within that system. But what you would have a problem with is when, for example, a government changed the regulatory framework, and suddenly that internal system would be affected by external events, and suddenly it would change. So the question is, how on earth do you start to encompass that in terms of a serious way of predicting the effects of what's going on in reality? How do you undertake the mathematics of this right from the first go? So the underlying understanding of this is that we have open systems. It's not a closed system. Real systems act atypically sometimes. And we often see that seems to be a non-causal effect. And the main reason why we have these kind of non-causal or seemingly non-causal effects is that we have numerous feedback loops making up the system ensemble. So again, if we refer back to the chemical example, it's the feedback loops that are controlling what's going on within this open system. So quantum mechanics, the work that Jack has done is founded on this notion that we not only have typical behavior in quantum mechanics, but we also have this atypical behavior as well. So the typical behavior that we see within quantum mechanics is essentially described by Born law, and this is something that you're brought up with as an undergraduate student, and this is kind of part and parcel of the accepted ideology. So the quantum equilibrium hypothesis can be stated in this way, that for an ensemble of identical systems, each having a wave function, psi, the typical empirical distribution of the configurations of the particles is given by this equation, rho equals psi squared. So the property had already been emphasized by de Broglie in 1927 at the Solvay conference, and was later used and formalized and given a much more detailed description by Durr. So one of the authors that myself and Jack have used in the past as a kind of reference material is one of the workers in quantum mechanics that has mostly worked on Bohmian type interpretations of quantum mechanics. And Durr used it to establish the typicality of empirical statistics given by the quantum equilibrium distribution. In other words, he formally started to describe within this quantum mechanical regime what we would call typicality. And the notion of equivariance is a natural generalization of the stationarity of a distribution in statistical mechanics and dynamics systems theory. So again, what's occurring is that we're looking at this perspective from a position of, again, Boltzmann-Gibbs statistical distributions. So quantum equilibrium invokes the typical behavior again of particle positions given a wave function. It also implies that non-equilibrium resides within the wave function. Again, so now what we're doing is going, okay, we have this concept, but how do we encompass something that's going to be real? And again, as I said just a second ago, this is resolved by use of a Boltzmann-Gibbs ensemble in first seeking a measure with which a statistical hypothesis about the typical empirical distributions over an ensemble of identical systems can be formed. Okay, so this is the kind of general framework that's being used. Quantum equilibrium hypothesis was presented in Bohm's original papers of 1952 as derivable from statistical mechanical arguments. Again, we're referring to Gibbs-Boltzmann. And this was further supported by the work of Viguier and Bohm's paper in 1954, in which they introduced stochastic fluid fluctuations that drive a process of asymptotic relaxation from quantum non-equilibrium to quantum equilibrium. So again, what is going on is that they're able to express what Schrodinger and Born did with regards to the derivation of this quantum equilibrium in a form which is associated with the Bohmian perspective. In other words, a Boltzmann-Gibbs ensemble. So if we have a look at the details of post-quantum mechanics, in Sarfatti's post-quantum mechanics, we have a feedback structure that mediates between the particle and the wave function. Again, I refer you to this paper that we wrote a number of years ago, and that gives the background mathematics of PQM. It talks about the work undertaken by Sutherland as well. And again, the idea is to understand the characteristics of this feedback structure and exploit its underlying mechanism. So this in a sense, the post-quantum mechanics definition is slightly different from other people's. For example, Bohm, because what we're talking about is two linear equations that are working between the wave function and the particle. So again, if you refer back to the chemical equation, we have this double-headed feedback loop. Now, we're talking about feedback loops. So a major driver in our previous research was the search for a predictive mechanism for these real life open systems. For me in particular, I was looking at financial stock market tracks, economic data. And these systems, you have to remember, are open. So in this work, we felt that real systems not only displayed fingerprint indicators of dissipative, fractal, and self-organizing critical phase change behaviors, but also exhibited the evidence of extremal, seemingly non-causal behaviors. In other words, outliers to the usual type of crash behaviors that you often see. So in other words, you were seeing crash behaviors, but in many instances, the mathematics, the underlying fractal mathematics that we were describing this were actually, in the reality, was demonstrating even greater crash type behaviors. And so the examination of the data from several studies, mostly financial data, suggested that what in everyday occurrence was modeled as a sequence, a system in equilibrium by the standard type of economic mathematics was actually being stoked or pumped to then exhibit not only crashes, but crashes that were even more extreme than generally predicted. So something interesting is going on in these systems. So what we were observing was, in a sense, a financial bubble. And these are behaviors where positive feedback mechanisms were stoking the system. In other words, we were observing behaviors caused by an attractor bubbling in a coupled oscillator system. So again, what we're talking about is not only do we have these feedback mechanisms, but we're now starting to think about the process of a series of points in phase space where the system, the elements of the system, are moving towards, in a sense, chaotic attractors. These attractor bubbles in generic behavior appeared in these networks of coupled oscillators, where the system typically orbits in an invariant manifold with an attractor where the peak trajectories are low, but is intermittently pushed into a region where orbits are locally repelled from the invariant manifold. So what this means to us is that real systems not only display equilibrium type activities, but also complicated hierarchical choreographies of phase changes within a far from equilibrium regime, much like those described by Ginzburg-Landau theory. In other words, what we have in reality can be described as a fractal system with these fingerprint behaviors. So the system is moving towards a critical point, like a phase change, but what happens on the other side of the phase change? Another phase change. So what's interesting about Ginzburg-Landau theory is that they start to talk about this process, numerous phase changes, numerous critical points within the system. And in passing, again, I'll refer you to the papers mentioned earlier to detail how this kind of maths fits into areas such as quantum gravity. we've started to look at the fundamentals of quantum physics in terms of this kind of fractal behavior. So again, I refer you to the two papers. So our main objective was to create a general formalism by which we can at least understand and ultimately control this feedback mechanism. One of the early people that looked at the mathematics of this was Per Back. Back was one of the founder members of complexity science, and his initial thoughts are published in his book, How Nature Works. So what we're now considering is what is the exact mathematics of this feedback structure. So how can we talk about it in a general formalism? How can we apply it to quantum mechanics in terms of how post-quantum mechanics is starting to describe this process? So this is a kind of general high-level perspective. What we do is that we determine a control parameter and a critical value for this parameter. We also describe the external driver and a mechanism by which we can have internal dissipation. In other words, what we're having is a memory effect across the whole or parts of the system. So the fundamental concept that we have to take away from this is that we have to take a complexity mathematics viewpoint. So if we consider, for example, the mechanics of consciousness, we shouldn't be thinking solely about dipoles. If you go to, for example, Hameroff's concepts of how consciousness arises, where what he talks about is, in a sense, dipole moments within benzene molecules that are acting like bits in a computer, zeros and ones. And while there's quite a lot of benefit from looking at this process, that he's undertaking, and he should be praised for doing this, what we really should be looking at is a fractal perturbation scheme, because if you look at real systems, they don't come in dipoles. We might have a system where we don't have a asymptotic series of multipoles. So number one, the simplification is looking at dipoles as opposed to multipoles. Number two, the simplification is not considering the fact that we have in a sense, a Taylor series of these multipoles, which may or may not be asymptotic. So in other words, a third element of a perturbation scheme might be larger than the second element. So we have to consider the type of mathematics and the mathematical, I suppose, tricks, if you want to call it, to try and work out what's occurring in these perturbation schemes. So, in a sense, the first port of call was trying to figure out whether there was a natural system that we could use as a kind of paradigm, and look at what was going on in this particular system, and see if we could get some kind of general mathematics to describe non-equilibrium systems as a whole. So the main notion, the most fundamental notion about the SOC process that we were referring to earlier is that of an absorbing state. In other words, something is occurring to this system, and we have a kind of possibility that we have a buffering from these external effects. So by changing the feedback relationship within these processes, we can move the whole system to a stable, far from equilibrium state. So in other words, if you have a look at, for example, if you consider crashes in financial markets, they are seen as not stable. So the idea is, okay, if we understand the drivers, if we understand the feedback mechanisms within these complicated systems, we can then start to control the events and hopefully predict the events that are occurring as part of these non-equilibrium, far from equilibrium states. So we have to observe non-equilibrium behaviors to produce an environment whereby the feedback structure is driven to a stable, far from equilibrium state. Why are we interested in stable, far from equilibrium states? Because far from equilibrium or non-equilibrium states have very, very interesting properties that we can exploit. And so if we can create a stable non-equilibrium state, then we can then exploit those behaviors, those interesting atypical behaviors. And there is one example of this process that Jack has already mentioned in the past, which is Froelich pumping. So Froelich had been working on the Raman laser spectre of some biological molecules, and he demonstrated that the characteristics of these systems were stable, far from equilibrium systems. So one of the kind of paradigms, examples that we're looking at, this is a real live example, demonstrates this kind of stable, far from equilibrium system. So what do we have? We have an absorbing state type feedback structure that induce SOC. This is non-linear behavior, and in turn this behavior generates a stable, far from equilibrium state. So all systems that replicate this behavior will have controlling equations that have the same form as the basic absorbing state SOC equations. So that's what we've got. We've got a set of equations, a set of mathematics that describe these type of systems across the board. So we're not solely referencing Froelich pumping. We're saying that Froelich pumping is an example in nature where we see stable non-equilibrium systems. So the understanding is, okay, this is an example of that. What we need to do is not only look at the mathematics of Froelich pumping, what we have to do is encompass that mathematics within a general formalism so that we can then exploit it. And the general formalism is complexity mathematics. So what I want to do is look at an example, because what's the background to this? Say, for example, I'm looking at a way to manipulate gravitational fields. Well, the way that I would undertake that is use an exotic metamaterial to provide an environment where I can gain these far from equilibrium stable states. And that is going to be an enormous undertaking. And it's been said in the past, this is kind of the Manhattan Project of quantum mechanics. So what I want to do is look at an example where we don't have to use exotic materials. What we can do is use the behavioral characteristics of quantum mechanical non-equilibrium systems from an algorithmic perspective. So if we go back to, just briefly, if we go back to some of the possible origins of things like consciousness, that is a non-equilibrium system, and the metamaterial is the elements of the brain, microtubules, that actually construct the environment whereby you can get this stable, far from equilibrium state. The interesting thing about some of the work that Hameroff has done is that there are issues with regards to the mechanism that's used with regards to microtubules and Froelich pumping. So again, there's some interesting explorations that I've done over the last couple of years that solve these essential problems that Hameroff has got. So what I want to do is look at an example where we don't have to use these exotic materials. And the example that I want to use is quantum computing. So quantum computing is going to be a world-changing, massive opportunity. People like Microsoft and Google are already putting vast amounts of money into developing these systems. And in the next decade, one quantum computer could be more powerful than today's entire global cloud. So that gives you an idea of the power of these quantum computers. What's interesting about what's going on at the present time? Well, in 2017, the United States government set up a series of standards. And what are these standards about? The standards are about how you can have quantum computers eavesdropping into current classical quantum cryptography. So what they're looking at is the dangers that quantum computers will have on the standard classical encryption processes. So the underlying understanding of this is that the mathematical problems that underpin a lot of the standard encryption processes can be used by quantum computers to solve using Shor's algorithm mostly. So the effects of this are obvious. So unless computing is complemented with quantum safe cryptography, things like forgery of digital signatures, decryption of previously encrypted data would be standard. It could occur. So obviously there's a heightened risk for organizations, both governmental and financial, and they have an incentive to secure this kind of classified information. So if we actually look at what these standards are, so this is the current state of the art. Much of computing, encryption, is founded upon the level of time that it would take to decrypt mathematically complicated keys. So many of the new decryption methods use a combination of mathematical tricks to try and get around the mathematics of the encryption, or they use computational muscle. So basically large amounts of computing power. So what these previous standards have undertaken is an attempt to preempt the ability of quantum computers being able to eavesdrop on encrypted data. So this is what we're looking at. To be clear, what we have is the possibility of quantum computers eavesdropping on the type of cryptography that's used in everyday life across the whole of the world. Why am I talking about this? Well, what happens if we start to look at actually quantum computing and cryptography within the realm of quantum computers? So at the present moment, if you want to use a quantum computer, a hybrid approach is undertaken, and you use your standard computer, your standard laptop, to communicate with quantum computers. And the underlying methodology is based on standard quantum mechanical frameworks. So in other words, you know that you're having your data eavesdropped, because what will happen is as soon as you perturb the system within a quantum computer, you will have a perturbation. So in other words, if you measure the system, that changes it, you will perturb it. So you will know as a person using these quantum computers, a business or a bank or something like, they will know that somebody has tried to eavesdrop. Now, the point about this is that the quantum mechanical framework that's being used at this moment for quantum computers is based upon quantum equilibrium. In other words, an equilibrium system, Born law. So currently, this is what's going on. So what can we do? This slide outlines the method by which we can use a quantum computer to eavesdrop onto another quantum computer. It has the advantage that we don't have to resort to specialist materials to induce a non-equilibrium state. Rather, you can use algorithmic methods to break into quantum computer encryption. So what we can do is algorithmically couple a not far from equilibrium, non-equilibrium algorithmic system to a standard equilibrium system type quantum computer and eavesdrop. That's just one of the examples that we can undertake using this methodology, and we're not using some kind of exotic material to undertake this. So you can see that from this slide, what we're doing is we're talking about the quantum mechanical realm. Okay, so in general, this is talking about how we can undertake the process. So as I said, we assume we have two ensemble particle systems, one with an equilibrium distribution. That's the thing that we're going to break into, and we construct a set of algorithms with a non-equilibrium distribution. We then use the non-equilibrium distribution to measure, in other words, couple with the equilibrium system, and we can describe the mathematics by an interaction Hamiltonian. The interesting thing is that the people running the equilibrium distribution system will have no idea that they're being affected. we can undertake this process without disturbing the wave function of the equilibrium system. So we can break into the encryption system. So this is telling you a way, not only how we can look at standard classical computing systems and they're being broken into by quantum computers. This is telling you what we can now do is we now have the mathematics to look at the way a quantum computer can break into and eavesdrop onto another quantum computer. So, in summary, the next steps. My next steps are to extend collaboration with Jack into his gravitational work, because, as I said earlier, I haven't focused on that. And so in the last few months, what I'm going to do, what I've discussed with Jack, is that I'm going to start to move into gravitational areas. In other words, develop the complexity mathematics side of this work into the work he's already done. I'm going to begin to publish work that I've undertaken over the last few years into consciousness. Again, I've just briefly spoken about that in terms of the work that I've done based on the excellent work that Hammeroff and Penrose have done. And the plan is to build upon the work on cryptography and exploit the level of pilot testing of quantum computational eavesdropping that's already been taken place. So that's where I am at the moment, and that's the end of my presentation. So if you've got any questions that you'd like to ask me, please feel free.
Maurice, that's wonderful. Thank you so much for presenting that. Let me do this. Let me stop your screen share. And
Yep.
I've enabled people to unmute themselves. I think Jose Rodal has had his hand up for a bit.
Yeah.
So
yeah. Let me just
see. I'll stop your share. There we go.
How do you do that, Tim, with the make a hand raise? How do you make the hand?
How do you? I would have to look that up. Actually, I don't have that one memorized.
Look at the horizontal bar in Zoom where it says reactions.
Thank you.
Okay.
Thank you.
Okay. Can I ask my questions?
You're a genius, Jose.
All right,
Okay,
let Jose, you have something to say now about.
Yes, I have two questions. Question number one, when you talk about consciousness, what is your definition of consciousness? And question number two, is it possible to determine if an AI system is conscious, and if so, how?
Right. Okay. Let me answer the first one. Okay. I look at consciousness from a perspective of the mathematics. Okay. And underlying that is the phenomenological perspective of Merleau-Ponty. So what do I mean by that? Is that if, say, for example, I take the situation where I'm driving in my car. So I'm driving in my car and I'm on autopilot. Yeah, I've learned the skills of how to drive a car. I'm sitting in the car. As I'm coming up to the lights, I see the lights on the back of the cars in front of me start to go red. So I know that there's a traffic light up ahead that's gone to red. So I have to slow. And I'm doing this without any kind of conscious notion. It's all on automatic pilot. Okay. So this is in a sense the way that, say, a neural net would work. Okay, I'm being very crude here because I don't want to wait. I don't particularly want to go into the hardcore maths of it. But what I have here is a system where essentially it's running on automatic. So information's coming in, it's being processed. I'm happy as Larry. Now, what happens when I get cut up by another driver? Suddenly, I get into a state where I have a subject and an object. The object being the driver that's cut me up, and the subject being me. So suddenly the system has changed. Okay, so what that means is that I have to have a mathematical construct that describes those situations. Okay, that's what's going on. So consciousness for me is the mathematical description of that process from a phenomenological perspective. So that's my starting position. Okay. Secondly, you asked about AI. Okay. Now, what you find if you take a human being and they're in an operating theatre and you put them under an anaesthetic, you can measure certain bodily functions. So you can measure their respiration rate, you can measure their brain activity, electrical brain activity. Okay. Now, these electrical brain activities have certain characteristic frequencies. Okay. So what Hameroff has done is start to look at these frequencies, because he's an anaesthetist. He starts to look at how the underlying mathematics produces these frequencies. Okay, so what I would suggest is that if you had, this is just a suggestion, I would suggest that if you had an AI that was conscious, what you would see are similar, or what you would be able to observe are similar frequencies within that AI structure as you would be observing in something like a human. So yeah. I don't know the differences between, say, for example, these frequencies for, say, my pet cat or a human being. Okay. But what I could say is that we could start to actually attempt to make these fingerprint frequencies. Now, let me say this, is that I worked a number of years ago in what was called forbidden transitions. So what was the actual work undertaking? The work was actually undertaking a mathematical process by which you attempted to predict frequencies that you were seeing in real life. So what I would suggest is undertaking the same process. In other words, what we have to do is undertake simulation modeling from a foundation of mathematics, and then apply that. So once we get the results, you know, say for example, I don't know, it's three frequencies, three characteristic peaks. Then what we could do is go to, so that's the result from my model. And then I go to reality and I go, okay, are those three peaks matching up with those three peaks that I see in reality? If they are, then the argument would be that the mechanism, the mathematical mechanism that I'm using, the narrative behind the mathematics is a good one to describe the data. If it's not, if the two don't match, the model's not right. I can't argue about, I mean, yes, I know there's stories about Richard Feynman where he was doing the calculations. They were incorrect as far as the experiment is concerned. They did the experiment again and they fitted with his calculations. Okay, I understand that. But in reality, what you're actually doing is taking the data, the best data that you can get, and matching it to your theory. So that's where I'm coming from with regards to that.
Wonderful. If it's okay, let me go to Michael next. I'm trying to move forward because we've only got 4 minutes until the top of the hour. Michael, go for it, sir.
We may want to go a little over on this one. It looks like a lot of people have questions, but I'll try to be quick. I want to follow up I want to follow up that question of consciousness. So, I mean, so classically speaking, with a neural net, you could have a neural net where some of its outputs are also its inputs. In that sense, it's similar to self-consciousness because the system knows what its outputs were in some simple sense. But that's not what we're talking about here in terms of consciousness as a definition. I think, is that correct?
Yeah, I think so. I think that what we have to do is take a kind of layered approach.
So self-awareness of that kind would not be okay.
Well, no. The way that I would see self-awareness, okay, is that here's one way that you could model it. Okay, is that I have a series of multipoles. So an infinite series of multipoles. Okay, so that's my baseline data set that's come in from the outside. Okay, and then what happens is I have another set of data, and that will change a corresponding infinite multipole series. So what I have to do is compare the two multipole series. If they're different, then what's occurred is that I've got new data from the outside. If they're the same, the data's the same. So somehow I've got to, number one, construct an idea, a concept that, in a sense, consciousness is described by these multipoles, and then I've got to describe a mathematical sense by which I can compare these two infinite series. That's how I see it. And those infinite series are constructed by the multipoles, which are in the essential mechanics of what's going on in a human brain.
And then one last thing about the consciousness, the resonances that we see, so like alpha, theta, whatever, delta, all the resonances in the brain, might those simply be like clock frequencies, like in a computer for
sure.
and timing?
Again, you see, is that I think that what has happened is that people have focused on kind of general areas, and a lot of the other kinds of mechanisms haven't really been considered. So, for example, we're talking about Frolic processes. We're talking about essentially a vibrational process, right? Well, what about vibronic? What's the effect of vibronic transitions within those systems?
Yeah,
Well, so for me, that's one of the first ports of call, is that, again, I start to chop up and then I think this is what happened with Hameroff, is that initially him and Penrose had a kind of general perspective, and then what happened was that people then started to comment, criticize, explore what they were saying. And if you have a look at Hameroff's later papers, the original papers was kind of like one silo. This is the mechanism that we're using, and then suddenly the silos started to increase. So I think that what is needed is a much greater overall framework by which these individual parts can be kind of, as I said, I'm talking about silos, can be slotted in.
Wonderful. All right. So if it's okay, let me go to and let me see.
I think this is productive. I think let maybe.
Can I just say one thing about this?
So Jack, we're at the top of the.
Yeah. Okay. I've given a very precise definition of what I mean by conscious qualia and described by section 7 of Paavo Pilkin's paper.
Yeah.
That's in term of Bohmian. Okay. So I want to, it's just the mechanism. It's a general picture of, based on the conjecture or the ansatz, the postulate that quantum wave functions are mental fields, and the reaction from the matter on the mental field is what creates our subjective experience of qualia. It's quite similar in general relativity to how the stressed energy tensor excites a gravitational field. So there's an analogy with gravitation, but
But,
let's leave
yeah.
it at that. Was somebody now? Is Larry going to talk now?
Yeah,
Is
so
it-
I think Larry's
let's
gonna talk.
let- yeah, we'll come
Now,
back
Dave,
to-
so
I think we
I
should
would
let
just
Larry
like to
talk.
ask if we consider the brain, the brain and the
Yeah, but let's not get
mind.
into that now, because let's stop this now, because Larry has to, we're running way over.
we're
Oh,
running a
are
little
we?
bit over.
Oh,
David.
okay, I can wait. We can wait
Just
till
one,
later.
just
Okay,
one
this is
point
the
I
thing.
would say.
We're not going to settle. We're
remember.
not going to solve
Don't worry.
the mind body problem right now. But
What
Larry-
I would
Okay,
say,
no problem.
just as a final kind of bullet point, is that what I agree with what Jack's saying. However, what I am doing is taking that from in a sense a complexity mathematics perspective. So in other words, for me, the narrative is undertaken by the mathematics. The way that I look at things is that if I look at the mathematics tells me a story. And that's what I'm interested in. I'm interested in designing the mathematics that then tells me the story, tells me the narrative, and then we can then argue about whether that narrative is appropriate or not. For me,
Mathematics is
as
the
with my
car.
theoretical physics
All right.
hat on,
I,
that's where
I
I
think
stand.
we should go to Larry. at
Yeah,
this
so
point.
let's go to Larry
Okay.
now. What I'll do is, Maurice, if it's okay, let me paste your email into chat, and people can email you
Yeah.
follow-up questions.
Sure, no problem.
Again, let me apologize to everybody for cutting things short. We're just trying to stick to
You're
our
right.
schedule.
I'm glad that it went on.
It was
for
great.
the requisite
Okay.
time.
Really
Thank
inspiring.
you.
So yeah, let's do this. Maurice, thank you again. Let's go to
My pleasure.
Mr. Larry Lemke, who has a presentation on, actually, and this one's really exciting. Do UFOs contain exotic material? And Larry, let me hand things over to you, sir.
Okay, so the title here is what was the Roswell memory foil made of? This is a work that I started on probably about 15 years ago when I was in a whole series of discussions with various people online, and everybody was trying to sort of come up with ad hoc explanations, about the memory foil. And so I decided to try to take a systematic approach, and kind of in each case dig down to sort of physical principles and see if there was a coherent story that emerged. So briefly, the outline here is that if you look at the body of all of the witness reports of the Roswell memory foil, there's approximately 24 of them out there, on the internet in various publications that have accumulated over the years. And then, of course, there are individuals such as myself and Jack, and I would guess others on this call that have their own individual witnesses that they know of and that are not public. So there seems to be. So the bottom line is there seems to be a number of people out there who are all telling kind of similar or slightly different versions of the same story. So what the point here is to look at each of and there's 6 main characteristics of the memory foil that have been reported. I'm going to look at each one of them individually. And the first question to ask is, for that particular characteristic, are any of those not explainable by conventional physics? If any are, then the next step is, well, what is kind of the minimum physical principle that you would have to invoke in order to explain that? It's kind of just Occam's razor. What's the sort of minimum new explanation that would be needed? And then once you go through that, for each of the 6 characteristics, you can then go back after the fact and ask the question, well, if you did need to invoke some new, physics to explain some particular characteristic, is that consistent with all the other characteristics? You know, would that negate some other, you know, explanation? And if you go through that process and the answer is no, it's all consistent, then you've got at least the beginnings of a story that could explain this set of characteristics. And if you do, then you can then attempt to match that to some kind of theoretical model for what's going on. So to fast forward, that's the approach I've taken, and I suggest that there is in fact a need to invoke a novel, you know, physical principle, and I'm going to propose a model to address that. Okay, so I guess I won't spend much time on the sort of the origin story of this memory foil. I'm going to assume that everybody knows that to at least some extent, that, you know, the bulk of the stories originate from the July 1947 incident that happened at the Roswell Army Air Force Base, and as a result of that, some 22 different, you know, witnesses over the years have come forward and told their little part of the story. Various researchers in this field have compiled that list, and you can, in the written talk here, you can get pointers to that if you're interested. Most of those stories were collected in the 80s and 90s, when the story sort of first became big in the popular mind, and there were a number of books, you know, written and so forth. But there's been at least one additional case that I find very interesting, which has only surfaced in probably since about 2016. And I will just briefly mention that one. In this particular case, there are these two children. One, they in this case, they're going by pseudonyms Jill and John. And Jill was 10 years old at the time, and John was 8 years old at the time. And they both lived in a little community called Page Manor in Ohio, which is a suburb of the Wright-Patterson Air Force Base. And the year was 1957. Now, I mean, they're literally just across the fence from the main runway and at Wright-Patterson. The girl's father was a major in the Air Force, and he was a pilot in the Tactical Air Command, stationed there. The boy's father was a colonel, and he was apparently an engineer and a scientist in what looks to be the Foreign Technology Division, which was located on the more secret side of the air base there. One day, the boy borrowed a piece of some mystery material out of his father's home office, and brought it to school one day to show to Jill, and said, you know, after school, let's go and, you know, play with this stuff. It was described as, again, a thin foil-like material, described as about 8.5 by 11, you know, roughly a standard, you know, piece of paper. And one of the things that makes this story interesting is that they got to play with it for about a week or so before John's father noticed that it was missing and came back and reclaimed it. So unlike many of the other witnesses, most of whom only saw the material or had access to it for a few minutes, these two kids apparently had it for, you know, 5 or 6 days, and were able to actually try a number of different experiments with it over that period of time. And they pretty much described what we see in a lot of the other reports, that you could crumple it up and, you know, throw it through the air and it would spontaneously go back to its shape, or you could crumple it up and lay it on a table and it would instantly go back flat. with no, permanent creases or anything like that. Seemed to be very strong. They would pound on it with hammers, try to cut it with scissors and knives, no effect. Put it under the wheels of a big heavy truck, nothing. Subjected it to high temperatures. That in the neighborhood where they lived, there was a gentleman who was who ran he was a farrier, which for those of you who are not familiar, that's the guy a blacksmith who makes horseshoes and stuff like that. And he had a forge, a typical coal-fired forge, and they would put the material in there. Again, no melting, no heating, no glowing or anything like that. But the one observation that really kind of sets this report apart is that the girl on kind of the last day that she had access to this material had placed it in the basket on her bicycle and was riding across a parking lot. And this was late evening, and it was dark, but there were street lights illuminating this parking lot. And she reported that when she got when this piece of material was directed in a certain direction to the street light, the light appeared to, as she described it, enter the foil and basically transfer along the surface of it and exit at the edge that was closest to her. And so it lit up, basically like my interpretation of that, it was essentially acting as a waveguide to the incident light, and translating across the surface of it. And so it lit up, and she never ever seen anything like that before, and it totally fascinated her. And so that's the interesting part of that one. Okay, so if you look at the basic characteristics, there's 6 of them that I've identified, and I've kind of assembled them in order of ascending strangeness. The first one, everybody agreed that it was a metallic appearance. Typically, gunmetal gray would be the descriptor that they would use. Everybody described it as lightweight, or technically, low density. Everybody described it as having high strength. Couldn't cut it, couldn't crush it, couldn't, people shot it literally with a 30-06 rifle, wouldn't penetrate it. And no one had ever seen that before. The 5th one is the one I just mentioned. It seemed to be optically active. It was not simply a monolithic piece of metal or something that just reflected, where just obeyed, reflection principles. And the 6th one, which I think is actually the most interesting, was this extreme heat resistance. Okay, so just kind of briefly, let's go through what is metallic appearance. Well, it's basically a shiny, lustrous surface coupled with high opacity. So, if you shine a light on it and look at the other side, the light won't come through. And it can be, it can only be like a sheet of aluminum foil, will do that. Well, so where does that come from? Well, ultimately, those appearance qualities of metals come from the fact that the metals are modeled as the so-called electron C model, where you have the core atoms of the metal, whatever it might be, aluminum or iron or whatever, are bound together, strongly in a matrix, an ordered matrix. But the outer valence electrons are not highly bound to those atoms, and so they're able to kind of float around in a non-localized manner, not attached to any specific item. So they form this sea of electrons that are kind of floating around against this background of the matrix. As such, that those electrons in the sea are able to absorb and re-emit wavelengths of almost all sizes. You know, they're not bound by strict quantum transitions, and so you get this ability to absorb and reflect basically all wavelengths, so it looks shiny. Also, when a photon is absorbed, it of course can reflect back out, but it can also emit back into the body of the metal. And again, since you have this electron sea, they're all absorbed, dissipated, and so a light wave can't make it very far through the body of it. So that's basically why you get the shiny, lustrous surface and opacity. And so, so the simplest explanation for the memory foil is that it simply had a metallic component. So no new physics required, you know, not very mysterious. Okay, now let's look at the low density. One witness actually reported seeing, bits of the memory foil floating on puddles, little puddles of water after rainstorms that had occurred out in the debris field for weeks or months after the actual, event. So that implies that the material, the density of the material was somewhere in the vicinity of 1.0. If there were no other considerations, you would say, well, okay, the fact that it's floating on water means obviously its density is somewhat less than water. But you can have other effects that come into play. For example, if the material was hydrophobic, it could actually float on the water and still be slightly more dense than water. You can see this with things like these water striding insects that can, float on the surface tension layer. And those effects can be additive. But the net result is that that tells us that the density is probably around 1.0 plus or minus a little bit. So there are really only three metals that are actually less dense than water: lithium, potassium, and sodium. They're all highly reactive. So that that certainly wouldn't explain it. The other thing is you can actually have voids within a material, right? I mean, if you take a piece of like foam or woven fabric made out of some material, the bulk density will actually be less than the density of whatever that specific material is, because you've got these voids in there, and if you average it over the total volume, it can actually be less dense than water, even though the parent metal that it might have been made from can be more dense, right? So, and by the way, some of the witnesses claimed that the so-called foil actually had a fabric-like structure. They claim that when you looked at it under magnification, it looked more like a woven material with very, very fine, fibers than it did just a simple monolithic material. Upshot of that is there's no new physics or anything required to really understand the low density and why it could float on water. Okay, high strength. Well, as I said, one set of witnesses reported shooting at the foil with a 30-06 rifle, which is a very high-powered rifle, and basically the foil would just spin up in the air and fall down, and they would inspect it, and there was no marks or damage or anything like that. Well, So that kind of behavior has actually been observed with like silk fabric or Kevlar fabric for other projectiles that are probably not as high velocity as a 30-06. So that characteristic by itself is not that mysterious, although in my estimation, the fabric to have done all the things that these witnesses claim, I think the material would have to be maybe a factor of 2 or so stronger than, let's say, Kevlar. Not infinitely stronger, not by a huge amount, because things like Kevlar and other high tensile strength metals even can exhibit this behavior of being very difficult to cut with scissors or a knife or something like that. So as we're discovering, having materials that are like maybe a factor of 2 stronger than let's say Kevlar is totally within the realm of theoretical possibility, and we're making progress on this kind of all the time. For example, nano engineered sandwich materials where you have different metals and so forth can achieve that kind of strength, right? And these are being engineered and experimented with all the time. Now, obviously, that wasn't available in 1947 just because of the technology. We didn't know how to do it. But I would say that there's no new physics required to explain that if you had the technology to actually implement it. Okay, now let's get to the shape memory. This is the characteristic that everybody kind of concentrates on. And I argue that it's actually, in many ways, it's, again, one of the least interesting or mysterious parts of the whole thing. If you look at the witness testimony, I assert that there are basically 2 different processes or different parts of that shape memory that were reported. One component of that story is that whenever you would crumple the stuff up tightly and allow it to re-expand, it would leave no permanent creases or wrinkles in it. So that's one observation. The other observation was that not only would it have no permanent creases, but it would almost instantaneously flow back. Witnesses often use that term, the flow back into its original shape, even if you like placed it on a table or threw it through the air or something like that. I believe that those 2 processes point to 2 different physical effects, and I'll get to that shortly here. So the first thing to recognize that every solid material has shape memory to some extent. That's simply a reflection of Hooke's law, which basically says that if you take a piece of material and you apply a set of forces or stresses on it, the material will deform, and that deformation is measured as strain or change of shape. And that for any particular material, there's a constant, the elastic modulus, that explains how much distortion you get for a given amount of force or stress that you put on it. And so, so basically all it says is that if you take a piece of material, put a set of forces on it, it'll distort and it'll change shape, and you remove that set of forces and it'll go back to its original shape. Well, that's shape memory. The trick is that there's a couple things about that. One is that's only true if the amount of stress that you put on it and the amount of strain that it experiences does not exceed a certain threshold value, which is called the yield strength, or the yield strain of that material. If you apply a force that's greater, that causes an amount of distortion that's greater than that threshold value, one of two things will happen. One is it'll, excuse me, the material will take a permanent step. It'll stay in a, excuse me, in a distorted condition, so it won't return to its initial shape, or it'll break. Or if you do it long enough, both of those will happen, right? So that this linear relation between forces and distortion only applies as long as the amount of distortion is within the elastic limit. It's called the elastic limit of that material. So I looked at how much strain, how much distortion would you get if you took, let's say, a flat piece of thin foil and folded it back on itself, and obviously that, you know, if you fold it back on itself, and this is what you could see if I had the slides up here, you'll have like one piece of flat material and a bend, and then another piece of flat material where it's bent back over itself, and there will be a certain radius or diameter of that bend. Okay, so what happens if you just keep making that bend diameter smaller and smaller and smaller? Eventually you get to the point where the top piece of the foil is lying on the bottom piece of the foil, and the diameter of that fold is basically the thickness of the material itself. And you can show mathematically that when you get to that condition, the amount of strain, the amount of distortion that you would have in that fold is like 100%. Okay, so the question is, well, what is the elastic limit for common materials? Well, most metals like aluminum, iron, brass, what have you, have a limiting strain of like less than 1%, right? So you don't, I mean, you can do, you know, you take a paper clip or something and you can bend it just a tiny amount and it'll stay bent, right? Plastics like acrylics and so forth can have an elastic limit of maybe a couple of percent. So they're actually quite a bit more flexible than most metals, but even so, you know, 2% is not a whole lot. Exceptional metals like nitinol was often proposed as an explanation. They have an elastic limit of maybe 5 or 6%. So still not even close to what you would need to be able to fold something up into, you know, tight fold and then have no permanent creases in there. So are there any materials that have a high elastic limit, greater than 100%? Well, yes, rubber is, latex rubber is the most common one. You can take a rubber band and stretch it to within to maybe, you know, 500% of its original length, and it'll return to its original length. It won't do it instantly, by the way, but it'll return to its original shape and size with no permanent, you know, deformations. So really, there's no new physics required to explain the superelasticity either. All you need is a material that has an elastic limit that's greater than about 100%. I don't know of any others than rubber, by the way. So there's no new physics required to explain that, but I don't know of any materials that existed in 1947 or even today that have this high strength and the high and the metallic appearance that would do that. But now let's get to the other element of the whole shape memory thing, which is that many witnesses describe that they would crumple this stuff up, put it on a flat like the table, and it would just instantly come back, flow back to its original position. Well, a piece of material like the thin rubber sheet won't do that. And the reason is because gravity will hold, pieces of it together. The only restoring force in a piece like that is the fact that the rubber itself is bent over, and so right at the bend you'll have elastic forces that want to restore it to its original shape, but you have the other piece lying on top of the other piece that resists that, and that friction between the two sheet, the upper and the lower sheet, prevents it from kind of like instantaneously flowing back to its original shape. So I believe that there has to be another set of forces that I think are basically surface forces on the foil that would allow it to essentially flow over itself and flow back to its original shape and do that quickly. So that to me is the first indication that there might be some physics here that are not entirely explained. Okay, then we have this optical waveguide part. It seems to me there are two sort of categories of possible explanations there. One possibility is, maybe it was a hyperbolic metamaterial waveguide that can support surface electromagnetic waves. That might explain it. The other alternative, it looks to me, is that there was simply maybe an index of refraction gradient near the surface of the foil, which could also, bend the light rays and perhaps cause them to transit parallel to the surface instead of getting reflected. Either one of those explanations is understandable now. In 1947, I don't think people were really thinking about nanomaterial, metamaterial waveguides, but certainly, a gradient in the index of refraction was known. That's basically, things like optical fibers and so forth. Obviously, neither one of those explanations was consistent with 1947 technology, but I believe that we could understand the science of them from our current perspective. And so at this point, I can't really make a choice between those. Okay, so now let's finally get to what I think is the good one, the heat resistance. There were many, or several witnesses who over the time basically had exposed the material to things like a kitchen stove, a natural gas flame, and a couple of them even claimed to have exposed this to an oxyacetylene torch. So an oxyacetylene torch has a flame temperature of around 3000 C. There are materials that can withstand an oxyacetylene flame, not very many, by the way, but there are 5 naturally occurring elements that would, and these are basically very high density, high temperature, high Z metals like tantalum, tungsten, osmium, rhenium, and so on. Carbon, of course, can. And more recently, there are super, ultra high temperature ceramics, the kind of things that are used for ballistic missile nose tips and stuff like that. they can have melting points above 3,300, C. All of those are brittle. So there are a few materials that could actually just withstand the simple high temperature, but that doesn't really explain what the witnesses were seeing, because any conventional material would still start glowing red around a little over 500 C. And by the time you got up to, 3,000 C, they would be glowing, bright yellow or white. So a conventional material, even if it had a high melting point, does not explain why you would not see any evidence of heat at all. Why you see no glowing, no emission of light. And furthermore, a conventional material, even if you heated it up to below its melting point, would still have thermal inertia. As soon as you took the heat away, you couldn't immediately grab it and hold it without getting burned. So a simple high melting point doesn't really explain it. The second kind of explanation you might think about is, what if the foil was a thermal superconductor? Okay, well, first of all, I guess we should note that we don't have any high temperature thermal superconductors. Liquid helium can be considered to be one within certain parameters, but and so what would a thermal superconductor do? Well, conventional materials require a thermal gradient between a hot spot and a cold spot in order for the heat to move from the hot to the cold, right? And this is why if you put a torch on a piece of metal or any other material like that, the hottest spot is right under where the torch flame is touching, and so that's the hottest. And in case of a oxyacetylene, that would be glowing, white hot, and then you'd get a radial, the temperature would decrease radially as you move out from that. A thermal superconductor, if they existed, would not change the fact that the material is heating up. It would simply say that all the material was heating up everywhere at the same rate and was always exactly at the same temperature. I mean, that's all it would do. But if you had a thin foil, thin piece of foil that was normal mass, normal matter, but it just simply was a superconductor, you would still be heating it up, and there would only be a certain finite amount of thermal mass there. And so if you took a small piece of this foil and hit it with an oxyacetylene torch, there would easily be enough energy there to heat the whole thing up eventually. And so again, you would see this phenomenon that it would glow, right? But it never did. And it also, again, never had any thermal inertia. You could take it right out of the acetylene flame and hold it, and there'd be no perception of heat at all. So now we get to my favorite theory, which is that the heat from the torch and these other sources, which were basically convective, heat transfer sources, never entered the material. And that would explain all of the observed phenomena. If no heat enters the material of the foil from the flame, excuse me, the foil does not heat up, it doesn't glow, it doesn't melt, and it has no elevated temperature as soon as you take it out of the flame. So to me, that's the only explanation that I've been able to come up with that explains all of the reported thermal phenomena. So how would that be possible? Well, a torch flame is basically an example of forced convection. You combust the oxygen, and in this case, the acetylene, highly energetic exothermal reaction. The reaction products are H2O and CO2 gas in an ideal oxygen hydrocarbon combustion. And those molecules, again, being polar molecules, first of all, they have high translational kinetic energy, and they also have highly excited internal states like vibrations and rotations and so forth. And then simply from the kinetic theory of gases, when those gas molecules would collide with any atoms on the surface of a material, they impart that kinetic energy, that stored kinetic energy, into the material, which then propagates through and ultimately results in heating and ultimately melting if it gets hot enough. If those gas molecules, those energetic gas molecules, never touch the surface, they never transmit that kinetic energy. By the way, I would note that this is exactly the kind of observation that Paul Hill made back in his work, published in 1995, about which he characterized as an acceleration field. Excuse me, I'm just getting over a cold here. So in his case, he looked at a rapidly moving piece of material, excuse me, which would impart kinetic energy into the gas molecules around it. We're now simply looking at the converse of that, where you have highly energetic gas molecules interacting with a solid surface, and an anti-gravitating repulsive field would stop that as well. In other words, the energy transfer would be stopped in both directions. Excuse me just a moment. So so that's my premise, that there was an anti-gravitating repulsive field near the surface of the foil. It would and it would explain the highly anomalous thermal behavior of the foil. It might also actually contribute to some of the other characteristics, including the low density and the high strength and the superelasticity, and maybe even the ability to act as an optical waveguide if it was in fact modifying the index of refraction right next to the surface. Okay, so now we're getting down to close to the end. So what could produce an anti-gravitating acceleration field localized right on the surface of the foil? Well, now Jack would say that obviously it was a engineered metamaterial, being pumped to create this anti-gravitating field. The problem I see with that is that the foil did not seem to have any obvious pumping, source. The foil was, presumably discovered in 1947 and handled as late as 1957. There was no obvious, power source that could have pumped it within that period of time. So if the foil was surrounded by this anti-gravitating field, it seems to be a static field and not a dynamic one. It's the DC component and not the AC component, right? So it looks to me like this could be explained if we assume the existence of negative mass matter, as discussed by Ludinger and Bondi and even Bob Forward and people like that. If it is possible to embed or attach negative mass matter to positive mass matter, then you could actually start to engineer structures in which you had a core of normal matter surrounded by a surface or a layer of negative mass matter. And the negative mass matter would be gravitationally repulsive, in all directions. Furthermore, if you had a mixture of positive mass matter and negative mass matter, that would actually reduce the apparent weight of that ensemble, because whatever the component of the negative mass matter was, when added to the positive mass matter, would go to zero, and you'd be left with a low density appearing material. So that could easily explain the low density, contribute to that. It could explain a hydrophobic surface, because it would presumably repel water molecules just as well as it would gas molecules in the atmosphere. And such a material would essentially be isolated from convective heat exchange with the atmosphere. Not necessarily radiative exchange, by the way, but convective. And then I've gone into a little sort of engineering exercise, and how could you build up structures with, assuming you could have these Bondi pairs, how could you build up structures? And I think you could do that. You could build little discs, and then you could string discs together into fibers, and you could ultimately take fibers and weave them into fabrics if you wanted to, and if you were able to engineer this stuff at the atomic scale. Okay, so that's basically the end of the talk, the end of the prepared talk. So at this point, I suppose we should probably go into Q&A.
Yeah. Now, if it's okay, Larry, let me thank you for that talk. It was absolutely wonderful and in depth. And let me apologize for the PowerPoint issues.
Yeah. Okay.
So will you be around after the next presentation? I think Arik is going to be talking about David Chalmer's hard problem. And I think we're going to have a lot of questions. I'm wondering if we might be able to do those a little bit later in the day, or
sure, like at the 12 o'clock.
Yeah. If you're open to it. Yeah.
Yeah.
Well,
I can certainly be around. Yes.
Let me go to Michael Perrone first, who has had his hand up for far too long.
Okay.
Thanks, Tim. So let's see. I wrote a few notes down. It doesn't necessarily have to be lighter than water if it's hydrophobic, especially because surface tension could keep it on top of water. So that's one thing that bears mentioning. And
can I respond to that?
Sure.
Yeah.
I did mention that.
Okay, cool.
Yes, I'm aware of that fact, that as I said, you can have things like little insects, that can walk on top of it. But
in fact, you can even do that with a paperclip. You can put a paperclip.
Right.
Yeah. That's irrelevant.
Yeah.
So and then when you were talking about elastic limits, wouldn't that be different for a woven fabric versus a solid foil?
Yes, it would. And I've considered that case. And in fact, a woven fabric actually makes the problem easier. If you want to consider a macroscopic example of a high elastic limit, just think about a screen door spring, right? You can take a spring, and at the macro scale, you can extend it easily more than 100% of its original length, right? Now, at the micro scale, if you look at the wire, you know, at the stresses in the wire, typically made out of spring steel, at that level, the wire is not undergoing any more elastic strain than it can stand, right? So at the micro level, the strain is still less than 1%, but because of the structure, you can add it all up and get, you know, over 100% elongation without exceeding the strain limit at the micro scale. So yes, and in fact, if it were a fabric, I mean, you kind of get that for free, right?
Yeah. So, and then the let's see. So that's there. The optical properties were interesting. I just wanted to mention that if you have some sort of optical waveguide on the side, the emissivity of the material could be extremely anisotropic. So if someone put it in a flame, it might only glow at the edges, and if the light's fairly collimated, they might not see it glowing. So yeah, anyways, if it's optimized for weird emissivity properties, that might be the case. And then the other thing is candidate material that no one seems to be talking about is borophene. Are you familiar with that one?
No.
So borophene is similar to graphene, but made with boron atoms, which means you have an extra electron to play around with.
Okay.
So when you intercalate metals into borophene, the sorts of defects that it introduces are much less relevant mechanically speaking than in graphene. So if you intercalate graphene, the macroscopic composition maybe has stronger van der Waals forces than it otherwise would, but it also gets a bunch of defects. And I mean, even so, even in those materials, the van der Waals forces seem to be distributed. But if you have borophene and you have extra bonding pairs of electrons there, you can get a stronger bond at the interface, and you can really, you can basically replace or tune with the loading level the van der Waals forces all the way to full bonding without removing the lateral strength.
So is this a way of explaining the high strength?
Yeah, it may, and also the elastic limit, because borophene has, in principle, up to like 100 times the strength, the tensile strength of steel. Yeah. Plus it can extend by 20% due to the way the bonds are arranged. Okay. So the elastic limit is very high.
Right. So I certainly would not exclude any ideas like that. I mean, you know, however, that still does not explain the thermal properties.
Well, I was thinking that is maybe more related to the emissivity, and borophene is fairly high temperature resistant. If you laminated it further with boron nitride or other materials, that would further increase the thermal resistance, and it might alter the optical properties to be what those people were seeing.
Right, but it would still glow if it got hot.
It depends on, so when you intercalate graphite, for example, it really alters the optical properties, and that may be the case for borophene as well.
Yeah, but it's still going to be a black body radiator, approximately.
That's not so clear. But in any case, if anyone's curious on making borophene and testing some stuff out, I've got a little lab. We can try things. We can poke around and see what we can make.
Larry, if it's okay, do you think that I could put your email in the chat? Maybe you and Michael could correspond on this.
Sure. Yeah.
Okay.
Yeah.
Okay. And again, if you'll be around in about an hour or so, and that way we can stay on track, because I think so. Okay. We're just about at the top of the hour. Jack had something very quickly. Sir?
Just a quick question. I just have a very, very quick question. Was that material tested for radioactivity emissions? Geiger counter?
I have no idea. I've never seen it reported. I've never seen anybody mention that. But
okay, because Eric Davis, one good thing that Eric Davis, I remember him saying at some point that there might be radioactive isotopes in the material he had, which would provide the pumping energy for, for my
Right.
mechanism.
Right. Well, we can talk about that later. I mean, there's a fundamental problem with that too, which is that in order for a radioactive source to be pumping, it has to have high activity, which means it has a short half-life, which means that it's probably going to, you'd probably see a decay in that over 10-year period of time. So I mean, I'm not in any way saying that maybe some of these materials didn't have radioactivity in them, but you have to take that into account. Okay, yeah, I'll be back in an hour.
What wonderful.
Okay.
Thank you so much. Thank you so
Okay.
much.
Let's take a 3-minute break.
Okay. And then I believe
break,
Arik is here. Let me double
Yeah,
check.
he was-
Yeah,
I am
he's-
here.
He's really here.
He's there. He's there. Hey,
Wonderful.
wait just a minute. I'll be right back.
Hey, Michael. Isn't boron a neutron absorber? That's what-
Yeah, it would
Yeah,
be.
and that's what they were having problems with at Chicago Pile 1 with Fermi and Szilard. And they had to get rid of the graphite they were using because it had boron in it. And they had to get new graphite. That was an
Yeah,
interesting
I think
recognize.
I think borophene, I've never heard of that before.
Yeah,
the
borophene. It would be an
Michael,
excellent mechanical. Oh, sorry.
Are there others that are similar to that? I mean, is it the graphene, but with boron? I mean, the next logical question is, are there like silicon or any others?
Borophene's kind of alone in that regard. It's basically so there's a class of 2D materials, obviously. Most of these exhibit high mechanical strength at very small scales, but it doesn't scale up because of defects in the crystal lattice and so on and so forth. But the boron has extra bonds that it can give up, and it will still retain a microstructure that looks like graphene. So like if you have graphene, you can have like a hole in the thing, and that's an area where a tear can start to propagate. But in the borophene, you've got this lattice, and then if you add a metal ion below that and you get one of the electrons off the boron, then you still have a hexagonal lattice. People have made borophene intercalants with aluminum, and it looks like graphene, but it's got extra bonds to all the aluminum. And then on top of that, you've got molybdenum diboride, rhenium diboride. A lot of transition metal diborides are layered. They're layered pieces of boron with the metals stacked in between them, and the boron's hexagonally arranged. They tend to be relatively brittle, but they're extremely high temperature resistant. So anyway, it's interesting in any case.
Yeah, it's intriguing. It seems like a truly 21st century material.
Yeah, I'm looking forward to more research in it.
Yeah, Jack let me see, you've returned, sir. Do you
Go ahead,
Jack, okay, should we go to Mr. Arik Shimanski now?
Hey, hi.
Okay.
Thank you very much, guys. Let me attempt to share my screen.
Wonderful.
You should be able to see the presentation.
Yeah, it looks perfect, sir.
Great, thank you. So what I'm going to share with you is the fruits of work for the last 7 months. And I presented it yesterday for the first time in the Science of Consciousness conference in Taormina, a shorter version of what I'm going to share. And I hope you're going to enjoy that. I'm going to discuss some of the physics, but if there are any questions about the fundamental element of the physics, I prefer Jack is going to answer them, because the focus of this presentation is going to be the work that I've done past it to try and integrate it into a broader picture that I hope proposes a solution to the hard problem, which is the current holy grail of consciousness science. So let's start, if you don't mind. So what we're going to have here, we're going to basically cover 3 things. We're going to show, first of all, that consciousness has quantum characteristics. The second thing in the program is that I'm going to use a theory and show that in my view, consciousness is the same all across the animal kingdom, which is a surprising result, and it was surprising for me also, and I'll explain how I derived it. And the last element is I'm going to present an attempt to prove that what we call phenomenal consciousness, which means our experience, actually stems a lot from retrocausality, and I'm proposing an evolutionary mechanism which is going to show how it emerged. And by doing that, we're solving part of what we call the hard problem, which we're going to address. So don't worry if you don't know exactly what it is. So let's start. And before we start, I'm going to share with you a little story. About 6 months ago, I was living in Paris, and we had a friend who was a real French raconteur. He liked good wines. He had a wine shop, and he liked good cheese. And one day he came and he showed us how to make scallops. I never had scallops that way before, where you basically open them up, you serrate them, and you put some lemon. For those who like it, it's delicious. So myself and my partner, that Jack has met, decided the next day, let's try it ourselves. So we went to the market and we bought some scallops and we brought them to the kitchen. And I didn't realize that the scallops were alive. So I kind of was trying to open it and shuck it. And as I was doing it, I could feel the scallop kind of resisting. It didn't want me to open, because obviously if I'm going to open it all the way, it's going to die. And I felt a strange feeling in my stomach. I had this kind of voice in my head, oh my God, the scallop is conscious. I can't kill it. And I must say I chickened out and asked my partner to do it. And in a sense, this presentation, what it's going to answer indirectly, I'll come back to the end, is the scallop conscious? And hopefully I'll share my conclusion at the end, and you can decide if you agree with me or not. So let's first of all provide a bit of background to what we're seeing here. First of all, I'm going to provide a few slides about the background of consciousness, because not everyone on this call are in the field. So the main question around consciousness is what causes phenomenological consciousness, which means why do we experience anything at all? Why do we need experience? If I see a red apple, where does the red come from? Do I need to see it? And the definition which is used in the field, which I don't really like very much, but this is the standard in the field, was coined in 1974 by a British philosopher called Nagel, which says that an organism is conscious only if there's something to feel like it being that organism. And it's part of this essay called "What is it like to be a bat?" And the idea is that something is conscious if there's an experience which is like to be that organism. And that is the standard definition. And that's a difficult definition because I don't think it's well-defined, no pun intended. And so there's a different ways to try and explain this problem. The most famous way was coined by a philosopher called David Chalmer in 1995. And it says, why do we need to experience anything? Why can't we have like a zombie that has the same wiring in our brain as we do and does everything we do, but just doesn't experience anything? What is the role of experience in our daily life, and why did it arise? And that's known as the hard problem. The easy problem of consciousness is what most people that are in the field look at, is what are the neural correlates of consciousness? So there's a lot of work about trying to measure activity in the brain. For example, a few weeks ago, I read that a machine was developed in Japan that you put some form of electrodes on the head and you show the subject's pictures, and without any training, it can actually recover very high resolution of those pictures. So, and being able to do that is known as the easy problem, because you're kind of showing, well, I found a neural correlate of what's going on in the brain, but I haven't really proven why that causes the experience of consciousness. So there's this gap, and they call it the quality awareness gap. And saying when we're aware of something, we see qualities like the redness of the apple, but there's no way that we can actually take up all of those little qualities like the redness of the apple, the blueness of the sea, and somehow sum them up into our experience of the world. There's no way for us to construct it easily. And there's this gap about how does this happen? I don't want to go too much into that because it takes too much time, but this is the setting of the problem we're trying to resolve. And there's quite a few physical theories that try to address this issue. There's what's known as the top-down approaches and the bottom-up approaches. And the name basically gives them away. The top-down approaches try and understand what can create consciousness from understanding the mechanisms of consciousness, how we think, what do we know about different parts of the brain and how they work together. I'm listing a few of them on the left. Specifically, if you look, I'm calling them physicalist theories. These are theories that believe that consciousness arises in the brain from physical interactions without any other elements which are not measurable. So the most famous ones are this global workspace theory, which says that there's like this central point where there's lots of different areas in the brain and they all work together. And one of them has prominence from time to time, and it actually fills the workspace, and that's what we're conscious of. One of the most popular consciousness theories at the moment is called integrated information theory by a neurologist called Tononi in Italy. And this one basically says the brain is very complicated, and we can see that a lot of the elements in it are holistic. So we're going to create a network of all the different elements, and we're going to see that some of those elements are irreducible. And he says those irreducible elements are called consciousness. And he says we can measure them using a number. He doesn't say why they're called consciousness. And I basically he's saying it's mumbo jumbo, but it's very popular. And it's an attempt to reverse engineer what consciousness is from qualities of consciousness. And the important one is the one at the bottom on the left, because I'm going to use it as a model for something I'm going to share with you later. The bottom-up theories include quantum theories, which try to explain what is happening at the lowest level in the brain. There's a new theory that's undeveloped, an Israeli physicist, that says you can use special relativity and general relativity to explain consciousness, but I also think it's a bit of hand-waving. And then there's neural computation theories that says we want to try and build neural networks that are more and more complex and see if we can come up with something that resembles consciousness, etc. None of those theories by itself provides a complete solution. Some of them seem to work better than others. And so coming back closer to our topic here, the second area of background I want to discuss is the quantum element. Before I'm going to go into Jack's work, I'm just going to mention the currently existing most popular quantum theory, which is called orchestrated objective reduction. And that's a theory that was developed by Roger Penrose. In 1989, he published a book called Emperor's New Mind. It's a great book. And then he followed it up with another book in 1994. And basically, he came up with this idea that he thinks that because of mathematical thought and the way that people solve problems, the brain is not computable, which means that you can't solve certain problems if the brain was like a computer, and we do solve them as individuals. Therefore, you can't use traditional descriptions of information systems to describe what's going on in the brain. And that was his starting point. And he developed this theory, which I think is very elegant, but I don't think is right, where he says, I don't know if you can see my mouse, but on the left, you'll have a system, you'll have a particle, and the particle is going to split into two superpositions, for example, and both of them are going to occur simultaneously as part of a mixed state of quantum physics. And eventually, they're going to start to grow apart in space. Now, he says, because those molecules are going to have a mass, a weight, they're going to influence space-time, and that influence is going to create some kind of a gravity potential, and that eventually is going to collapse those two superpositions into a single state. And he even gives a formula on the right to more or less say the amount of time the collapse will take is a function of the gravitational energy of the system. The claim that Penrose made was that that act of gravitational collapse, which he's the first person that kind of came up with, is the consciousness as we feel it. Again, it's not a proven, or there's nothing that actually shows us the case. His intuition is that he says this collapse is an uncomputable event, and therefore it can lead to consciousness. And then Hameroff is the one that introduced the ideas of microtubules that Maurice mentioned earlier, which I'll very briefly touch on. And he contacted Penrose after he read his book, and he says, I've got a candidate for where in the brain we think this might happen. Microtubules, for those who don't know, are in a sense, the scaffolding of the brain and of the neurons. These are very, very long, if you want to look at them like channels that are made up of a protein called a tubulin. And you can see in this example in the middle, they sit inside the neural pathway. They got water in them, and the water can conduct polarity, they conduct electricity. And those pictures that you see on the right, those black and white patterns, are the different monomers of this tubulin, and it creates patterns that basically go up and down. And measurements in the last 5 years, which Maurice mentioned, shows that they got a variety of resonant frequencies that occur at different levels, up to terahertz levels. And a lot of people believe, in some cases, those resonance frequencies show collective effect that can go over time. And Penrose is the one that initially mentioned Fourier condensation as a possible mechanism for long-term coherence in a living environment. So this is currently the most viable, not viable, but the most popular theory of quantum consciousness. Penrose is going to talk here on Saturday, and what he's going to introduce, which I was quite pleased to hear that because I wasn't aware when I actually prepared this material, that in order to resolve some of the problems around his collapse of the gravitational induced collapse, you have to introduce retrocausal calculations to remove dissipation and heat from the equations. So he actually believes now that you need retrocausality to create self-consistency in his own theory, but for other reasons. And so we're going back to the bit of work I did with Jack around 6-7 years ago. We met in London, my common friend, and we met a few times in London. We actually had a very nice supper with Hal Patnoff and Kit Green, which I'm going to mention later. And we also met last year in San Francisco. And the work that Jack did a few years ago was around developing some ideas around PQM and then applying them to the idea of consciousness. And I'm going to be using some of those insights in this talk. And some of them, to be honest, I only understood recently about 1 or 2 of them. And I think they make amazing sense and they're very elegant. And I'll mention them when I get to it. And so PQM is a name given by Sarfatti to a few insights that are provided. And if you don't mind, I'm just going to stop. Don't worry. Okay. So I'm not going to go to all the details, but the idea is that through the work of people like Roderick Sutherland and other people, it's become possible to describe a Lagrangian of a system which is quantum in nature, using Bohm's pilot wave theory and using Aronov's two-state vector formalism. Now, I'm not sure if everyone is familiar with it. I didn't really go into any details in it, but essentially the two-state vector formalism says that the present is a mix of quantum wave from the past and what Jack likes to call a destiny wave from the future. So the present is actually a mix of future and past wave functions that mix together. I think it's a beautiful theory because it reduces a lot of the problems that we have in quantum mechanics today. And in a sense, you end up having to make 2 choices. You either give up locality or you give up the direction of time. And both of them lead to consistent theories. Current quantum physics gives up locality. Using the two-state formalism, we accept waves coming from the future, but then we don't have any non-local effects of suddenly impacting a proton 10 light years away. And I think this is really a much more elegant way to look at it. But coming back to where we are, so Sutherland showed that you can take a system and you can combine this Bohm pilot wave theory, which deals with real particles in a relativistic framework with this two-state vector formalism. And then he did something else. He showed that you can also include what's known as bibbles. Bibbles, again, is a term that I've learned through talking to Jack. It's a term developed by Bell from the Bell inequality in, I think, 1970, where it's the kind of the part of a system which behave in a classical way, i.e. they're not quantum. And all this mishmash together means that you can put together a classical system like a nerve and a quantum system like a wave, and treat them together in a self-consistent way. And it deals with a lot of issues, and I haven't really seen anyone do that. So I think that the principle that this can be done opens up a lot of possibilities in understanding how real world physics work. The second thing that Jack introduced, which I really think was great, is this idea that if we look at gravity, and you know, we all sometimes, when you go to the planetarium, those of us who still remember going to a planetarium, you sometimes see those very nice funnels that you can take a coin and it goes around and around and around and comes down because it imitates what a gravity wave looks like. Einstein's action-reaction organizing principle is around the fact that when you have a body that has a mass, it impacts the space around it, and is also impacted by all the bodies that they have their own mass. So essentially, it's both impacting the world and it's impacted by the world. And what Jack was saying, you know, in quantum physics, mostly when we have a wave function, it impacts the world, but we don't really take into account the kind of back reaction that would have back on that body. And that doing that adds an extra level, which introduces something that I'm going to mention now, which is quite exciting in the context of what we're talking about. Now, Jack, by the way, if you feel that you want to jump on the physics side, feel free, but if you want, you can also do it at the end. I'm not really going to run into the equation. The idea, though, is that in general, unitarity of the system means that what we call the pilot wave is the information wave that drives the particles and gives them access to the information about quantum interactions. And it has to be conserved in order for the system to behave in a certain way. And if you include those back reaction, it kind of breaks that unitarity principle, which what it does, it leads to those three outcomes at the bottom. Those outcomes is really what's important for anyone to remember from this section. The first outcome is that the quantum system with bibbles, which means with classical elements, can be described using the past and the future. It may lead to the breaking of a Born rule. And that is important because under certain conditions, if that happens, it leads to something called entanglement signaling. And in our context, it means that it's possible to send information using those waves coming from the future, if there is something that the system can occur. And this is something new that came from the work that Jack did. And this is really, I think, the key for what I'm going to present later. And so Jack had this insight. He says, you know, this information wave, which is been kind of derived by Bohm, reminds me a bit of the kind of information that you can have when it comes to consciousness and how consciousness can impact a living organism. And the back reaction changes that information wave. So the insight that Jack had is, well, this back reaction, this effect of the field on itself, on the particle, is really what causes consciousness, or let's say causes life that leads to consciousness. And that is a completely new idea. I've changed it a bit in the end. Forgive me, Jack, but we can discuss it later. And so let's kind of talk about how can you look at a quantum system and say, this is something that's going to help me describe consciousness. What you see here is a diagram that shows you the scale of the human central nervous system. So here it starts with molecules, so it's already a high-level system compared to atomic, subatomic particles. And you can see that when you get to neurons, you're already many, many degrees of order of magnitude higher than traditional quantum effects. And when you go up to systems of the whole nervous system, it's a very, very, very high level, very complex system. And closing that gap is very challenging. And I think this is a lot of the challenge of a lot of those quantum type theories, because people have ideas about how things can happen, but there's no real proposals of how to do that. And really what it means is that quantum theories happen to operate at a very, very low level, and they don't seem to kind of meld into any of those what I call top-down theories that try to describe the operation of consciousness as in a larger kind of a way. And you need to integrate those levels to be able to provide a full theory. And I'm going to attempt to do that in this presentation. So let's go to the first, and actually the easiest and shortest part of this program, the assertion that consciousness has quantum characteristics. And I'm going to use two arguments to show that. The first argument is based on an article that was published in 1979 by Benjamin Libet. Benjamin Libet became very famous because he's the first one that did the experiment that showed that if someone wants to do something, let's say move their hand to pick up a glass, the nerve signal is identified in the brain by about a second before the actual person is aware of their intention, and led to a lot of issues around the issue of free will. This specific experiment have a lot of other explanations now, but the experiment we're going to discuss now is a bit different. What Libet did, he says, let me try and think what happens when I touch someone in the hand or when I use an electrode to excite their brain. And what he did, he had patients that for medical reasons or epilepsy mostly had to have electrodes in their brain. So what he did, he says, okay, I've got a system of measuring when someone says they're conscious. So what you see here on the top picture, the one that says A, he has an apparatus that touches the person on their hand. And when it touches the person on their hand, straight away the person says, oh, I feel something. So there's hardly any gap. I think the gap is 30 milliseconds. And then he goes to the place in the brain that actually processes the signal that comes from the hand, and he starts an electrode to stimulate it. And he says that up to about half a second, nothing happens. And only half a second where you can see this potential slowly building up, he calls it neural adequacy, only then the person says, oh, I feel something. So when you touch physically, you feel it straight away. When you use it, use a brain electrode, it takes half a second. Okay, that by itself is fine. But what happened is, and this is what happened in section D, is something really weird. What happened in section D is that the automatic apparatus touches the hand of the person, and after 200 milliseconds, which means less than the 500 milliseconds, it starts to stimulate the brain. And when that happens, the person, even though you touched him before, doesn't report that he felt the touching. It only reports it after half a second. So let's try and think about it. If nothing happens in the brain and I touch your hand, you feel it straight away. But if 200 millimeters after that start to stimulate the area, I don't report the touch that happened 200 milliseconds before. It's as if the effect, the interference in the brain gets transmitted backwards in time and informs the system that nothing happened. And only after half a second, you feel the touch. And this is very similar to a delay choice experiment, which we know in quantum physics. And this is already published in 1979. People replicated it, and no one's ever shown that it doesn't work. And I'm not aware of any mechanism in nature besides retrocausality in quantum physics that can explain this kind of behavior. So that's the first clue, in my view, that consciousness has a quantum element in it. The second element is something that a lot of people are really familiar with. I have three areas in the slide. The first one is the huge amount of precognition experiments that were done. I saw a talk, by the way, Jack, with Daniel Sheehan yesterday, and he talked about a new kind of precognition experiment, which blew my mind. I don't know if anyone, if you ever heard of it, it's called a tripartite precognition experiment. So think about it. Newspapers publish pictures in the sections on a daily basis. So a lot of newspapers publish a daily picture from AP that describes somewhere in the world. So what they did is they took a person and said, in a day or two, this paper is going to publish a picture. I want you to draw what you think this picture is going to be. And they seal the picture. And then the picture comes out, and you can see that this drawing is very similar to that picture. The reason why it's a triple blind experiment is because the picture that is in the paper has not yet been taken. It's only been taken the next day because these are daily pictures. So it removes this idea that maybe someone has that knowledge and somehow you can communicate to it. It's truly an event that happened in the future. Now, I'm not going to go into more details, but there's a list here of at least 3 articles. One of them is with Julia Mossbridge. where they actually collated, done a meta-analysis of a lot of precognition experiments. And I think anyone who reads the literature and is intellectually honest can't ignore the fact that it works. The bottom line is something that obviously Jack is very familiar with, is his work and other people's work with the Stargate program and the remote viewing issues. And anyone who's read those accounts also, I think, has to be intellectually dishonest not to accept that remote viewing is a real possibility, and you need some other mechanism in the world to explain it. The third element, personal experience. I'm not going to go into it, but I personally was exposed quite a few times in my life to events where other feeling from a distance or very clear predictions of the future. So all of those all those non-local and non-temporal events cannot be explained unless you have some sort of quantum mechanical underlyings. And I think all of those things together, what I call curated evidence, supports that and consciousness occurs, and it possibly has a local retrocausal nature because of those experiments. And only quantum theory can currently support this. I just want to make a quick comment. I personally don't think that non-computability is a strong enough reason to go quantum. And the reason is that we know in science that when you look at, let's say, a problem and you run out of ideas, a lot of the time you can look at something completely different and use allegories, analogies, or other things to kind of take ideas across from one field to another. And it's a separate process than trying to solve a non-computable problem from a Gödel's perspective. But I'm not going to go into that now. But I think that all those other things together at least convinces me that consciousness is a quantum element, which is very strong. The second thing we're going to now discuss is how do we marry quantum physics, a quantum consciousness, to a top-down theory. And to do that, I'm going to present a top-down theory, which I think is a good candidate to be connected to a quantum underpinning. And I'll explain why it's a good candidate. The theory is called predictive forecasting. And actually, part of it is going to answer one of the issues that Maurice Passman raised earlier about the driving of the car and suddenly seeing the red light or something changes. So, and the goal of this section my goal was, how do I identify a model of consciousness that can be a candidate for quantum integration? And I first came upon this by a really excellent book called The Hidden Spring by a psychoanalyst, neurologist called Mark Solms, and I suggest everyone who's interested should read it. But the idea behind this theory is that the way the brain works is the brain doesn't actually have a model of the world. The brain continuously creates predictions about the world. So we have initial sensory information coming in, and we start to use the memory, and we start to build lots of models. And those models try to fit the world to our experience and what we think. It was first developed by a guy called Friston. Anyone who's interested, he came up with used this beautiful concept called a Markov blanket, which shows how a collection of cells can actually start to have a memory and models of the world. But the idea here is that what we do is based on prediction and inference, and there's hierarchical processing of the brain in the brain. And from a physics point of view, the point of an organism and the point of consciousness is to minimize free energy. And the way it does it is by trying to reduce the prediction error of the system. And it's a bit much, but as I talk, you'll see what I mean. And Solms took it forward and he identified the location of consciousness in the brain. And this is why I like this theory and why I think this theory is a great candidate for integration with quantum physics. So Solms, what he did is he said, there's a set of this system, you see this line here, it's called the reticular activating system. And this is a part of the brain that sits in the middle, and it's connected to two systems. It's connected to the autonomic system, which gets all the information from the body, but it also has all the information from the cerebellum that comes down and meets here. And what experimentally was shown that there's an area of a few cubic millimeters in that thing that if you interfere with that area, consciousness is lost immediately. And also psychotropic drugs affect that specific area. So a lot of the drugs we use as mood stabilizers or for other disorders actually affect there, and they seem to have a very strong impact. And his view was that consciousness comes from affect, from feeling, that this is what allows us to feel our way through. And the reason for that is that, and now I'm going to come to Maurice's example. Let's assume you're driving your car and you see people slowing, you slow down, everything looks the same. And then suddenly something comes from the right. Up to this point, you didn't need to change your model of the world. Everything that's been happening has been happening like it's been happening to you millions of times when you drove a car and you slow down at a traffic light. The minute something comes in, your model of the world doesn't work anymore the way that it used to work. You have a prediction error. Your initial model of I'm slowing down to a traffic light and everything is fine is no longer accurate. So consciousness is what comes in to actually allow you to fix your prediction error, to say, okay, well, what's going on? I need a new model. Oh, this is car coming, is it going to hit me? Whatever. And that improvement of prediction, according to that theory, is consciousness on a high level. And I think it's a beautiful theory because I think you can fit it to a lot of experience that we have as human beings. And this is a known picture, it's known as the triune brain. And it says the brain essentially is what's the reptilian brain, the mammalian brain, and then above it is the primate brain, which is most of our gray matter sits. And that area that we're talking about, which Sohm believes this is the little pocket of gray cells, which is consciousness, sits here in the reptilian brain. It is part of evolution from the beginning. And so to give it a high level picture, we have your consciousness sits here in the middle, and it sits between two systems. We have the autonomic input system. And the reason why it works is that when you walk around and something happens and it's urgent, you need to react before you think. And so, for example, if you walk and suddenly something goes into your visual system, your system is going to actually start to turn your body automatically before you're even aware of it towards whatever the threat is coming from. But we still have to make sense of what it is. And making sense is what happens in a cortical input, where we actually analyze the world, we see what it is that's coming, and then we can respond appropriately. So consciousness kind of sits in the middle between this very quick autonomic or instinctive responses and those, if you want to call it qualia or thought out responses that give us context, that kind of top of the model that I mentioned. And this kind of made me think, you remember the beginning of my story is like, ask Caleb's conscience. I'm kind of thinking, what makes human consciousness special? And one of the things that came to my mind is, how much information do we have in consciousness? Because we take it for granted. We look in the world, we see quite a complex picture around us, but our picture is a picture that we build. We don't see everything at once. So I was asking the question, how much information is there actually in our conscious focus? And I did some research. There isn't that much written about it, but the things that are written about it are quite surprising. So the human temporal resolution, which means if things change around us, how much information can we absorb, is 60 different bits of information per second. And if you think about it, for such a complex system as the brain, it seems quite low. In terms of traditional psychology, the psychologists say we can have 4 chunks in memory. And in terms of a lot of other research that was done, depending on the context, we can hold between 3 to 100 bits of information at any given time. And from a visual point of view, we need about 11, 12 bits of information to create a picture that's meaningful. Now, if you think about it, this is a really, really small amount of information. And the motivation for me for looking at it is, if we can build a quantum system that can model a consciousness, we want it to have as fewer components as possible. Otherwise, it's too complicated. And in this case, I found it very positive, because if consciousness is such a small amount of information content, it's going to be less difficult to build a quantum system that actually mimics it, because the number of free variables is very low. The conclusion that I got from that is that because the information content of our consciousness is very low, it can't really be a good candidate for differentiating between humans and animals. Because, if we only have 3 to 100 bits of information and 11 significant bits, how low can it get for a mouse or a rabbit or a cow or whatever? So I was trying to think, what does that mean? And I just want to make a distinction between the content of experience of conscious experience and the information content of experience. And I'll explain what I mean. Information content of experience is how many bits I can see it every second. The content of experience is everything that kind of gets built together, which is obviously much more than that. And that leads me to what I call my radar analogy to consciousness. So you see on the left, this is like a radar. And the way radar works is got this very narrow beam that scans the area. And whenever it hits something, it kind of creates a picture. And so our consciousness, in my view, looking at those approaches, is like this narrow beam with a very small window of information, and it scans. What does it scan? It scans the input that comes from our brain. And so it basically gets all the input in our brain, and it builds a picture of reality which is rich, but the actual door through which this picture is built is very, very narrow. And all organisms share this structure. The structure that I showed you with the two pyramids can be shared by all organisms, because all organisms have this autonomic system, and all organisms above a certain complexity have the cortical system, the brain. And the best way to think about it is, this is a dumb computer terminal. I'm calling it phi because this is consciousness. On the left, we have a bat. A bat have got about 5 million of what's known as sensory associative neurons. These are the neurons that sit on the top of the head and actually gives you intelligence. Humans have about 20 billion. And so, but you can have a dumb terminal and it can be connected to an abacus, or it can be connected to a supercomputer. You're still going to see the information to a dumb terminal. Here, you're just going to see it faster and you're going to see more of it. And I think this is the model of consciousness. And so the last part, I'm going to show how this arises from retrocausality, and I'm going to propose an evolutionary mechanism that explains why we're conscious, why it happens in the first place. So I modified Jack's idea slightly, and I'll explain in the details why I think it works. I think that retrocausality is the primitive of consciousness. So the back reaction, I think, allows for the information to flow, but the actual primitive here is the retrocausality. And I think it seems crucial because it allows us to integrate the senses, and I'll explain why. And it also provides an evolutionary advantage. And this diagram essentially shows the whole picture, and I'll go step by step. So let's assume first we have a sensory input. It's step one. It comes into the system. So what normally would happen is that because our brain is very complicated, they have to compile a lot of information from lots of sources, and they have to make sense of them. And that takes time. This is the 500 milliseconds that Libet kind of call neural adequacy. And this is the time it takes to take the information and process it and create an internal model of that, which is the qualia, what we feel. This is the redness of the apple. And when that model is built, and this is going up, if you remember, I showed you this pyramid of models that gets built according to this theory. When you get to the point where you have to make a choice to improve the prediction, that choice is a wave collapse event, which happens here at point 3. And the difference between that and Orch or Penrose's theory, Penrose says the wave collapse is consciousness. I'm actually, this is, I think, really, Jack, was a great idea that you had, is kind of I realized this is what you meant. I only realized it recently, that what happens then is there's a retrocausal event that goes back 500 milliseconds to where the conscious event happens, which is what we saw in the picture, that the person feels it. Now, Jack had this intuition that I didn't understand until recently, that consciousness and that weak measurements are an important part of the process. And I kind of didn't really understand why weak measurements. And then I got it. And the reason is that the wave collapse happens here. This is where the information is. But if consciousness would also happen here, then we're not going to have this effect of retrocausality that will allow us to do this. And if the wave collapse happens here and the information goes back, this is where the weak measurement occurs. Weak measurements, for those who don't know, are a way to prod the system to get some information about it without disturbing this, without a collapse of the function. And because this event happened, we can now have a back reaction with the information back to the conscious moment, and we can use it in order to survive. And this really comes to the evolutionary mechanism. I'll come in a moment. Before I get there, I'm proposing that two types of conscious experience is sensory experience, which is really what happens when we see things or people touch us, and they really require this retrocausality. There are reflexive experiences which come more slowly from the brain, and I think they might have an element of that, but it's just not as pronounced as before. So the model of consciousness, the full model, is like this. What we have here, we have from the bottom the input of the body of autonomic input, that's immediate input from the nerves. We have the input from the brain of all the qualias. We have in the past all those projections, what we think is happening in the world. And then when we actually become conscious, we have this retrocausal qualia that allows us to take this insight and bring it into a present moment of consciousness. And why would it give us, why would it evolve, and why are we conscious in the first place? And by the way, there was a guy in this conference, a British philosopher called Nicholas Humphrey, who actually suggested, and I kind of agree with it, that we should change the terminology a bit. And when we say consciousness, we actually use sentience, because I think that's what we really mean by that. And proto-consciousness should really be cognitive consciousness, but it's a numerical thing. So let's look at the picture on the left. Let's look at a bat. A bat is going to have quite a large number of sensory inputs and a much smaller number of cortical neurons which deal with thinking. And if we think about it, the bigger your amount of neurons in your cerebellum, the longer it takes for the processing to occur. So it's going to take longer to build up that potential. So an animal which is just evolving and it's just beginning to have some kind of what they call the sensory associative neurons, which is kind of the cortex neurons, its processing is going to be very, very fast. So there's always going to be, but it's always going to be slower than what comes straight up from the body. So there's a gap between what we feel when someone touches us and how long it takes us to think it through. Now, this gap means that it takes a little time to understand what the hell is going on. Now, if this gap is too long, we're going to die. Because if we walk in the jungle and a tiger jumps on us, and it takes us half a second to work out it's a tiger, by the time we worked it out, he ate us. So there's a minimal amount, I call it the TE, the survival gap, the evolutionary gap, that if an organism takes more than that to process, they're not going to continue surviving. So evolution has two options: either stop growing the nerves, or be able to select for a mechanism that actually has some retrocausality that closes that gap. And in my view, that is the key for the emergence of sentience on Earth and for the development of consciousness. But this is also the why of why qualia take place. So qualias are more complex representations of the outside, and they can take place because we managed to have a longer gap that allows us to process it better. And this is the first time that I've seen at least an evolutionary explanation of how consciousness can somehow interact with this quantum explanation and provide also a reason why it occurs in the first place. And so we have a long evolution. You have this continuum. We have life, which depends how you define it, like whether it's a molecule or something else. Then we have what's called a pro-consciousness. So animals that have a nervous system, but they're going to have what's known as ganglions, which are a collection of cells, but they're not going to have like a brain. And then at a certain stage, when the gray matter starts to grow and the gap gets bigger than this evolutionary gap, the jump occurs and we go into retrocausality, and I think we develop sentience. And I think probably bats are the lowest level animals that have sentience, looking at the amount of neurons that they have. And coming back to the scallop, because I'm sure we're all holding your breath to know whether the scallop is conscious or not. So scallops have a neural structure with 3 ganglions, which means they've got 3 collections of central collections of nerve systems going in. The other thing is scallop, I don't know if you know, but the shell of the scallop is full of little eyes. And those little eyes also combine together for a little bunch of neurons. But actually, just there aren't enough neurons, in my view, to process in a time that's going to give a delay. So I think that scallops are actually not sentient. So they might be cognitively conscious, i.e. they know when to open and close or move, but they don't have sentience in the sense that scallops don't have an internal experience because the system is too close. So I'm feeling much less guilty about killing a scallop. So I guess this is the last slide, and I'm just going to quickly discuss 3 areas, and I'm happy to touch on a 4th one, which is quantum computers. This work took me to places I wasn't expecting, and I'll explain what I mean. When I developed those ideas about the narrow field of consciousness, it started to make me think about meditation experiences where people talk about deep meditation and you have this state of no mind. And it made me think actually consciousness might have no content at all, because it's something that happens at the moment and we populate it with what we see from our brains. And my current view is that this retrocausal effect is like a key. And when this retrocausality happens, something comes in. And I think that something that comes in is a panpsychic thing. It's a connection to a greater consciousness. And this retrocausality opens the door for that. And that's why sentience is a connection to greater consciousness. And another way for me to think about it, because I've read books like The Secret Life of Trees, that I think plants have some consciousness, but I think it's a group consciousness. I don't think it's individual consciousness. So this retrocausality creates individual consciousness, which is the best metaphor I have is if you think of a black screen with a very strong spotlight behind it, every time that happens, you prick it and light comes in. So there's one source of light, but they come in different places. And I think this is what is consciousness, which is not what I was expecting to find when I started this. And that is similar to some feelings I had and some reports people have. When it comes to artificial intelligence, it is also interesting. If you follow my argument, most of what we think as thinking is the brain, it's not consciousness. And so, yes, I believe that we'll be able to develop computers which are going to be very intelligent, much more intelligent than us. But I don't believe we're going to achieve the phenomenal experiential idea of consciousness within a computer unless we can somehow find a way to completely model that with physiological mechanism that creates a back reaction. So I think artificial intelligence is going to be massively intelligent, but I don't think it's going to be conscious the way we understand it, even though it might not be possible to tell the difference. That's the truth. And the last point, as I mentioned about quantum computers, this is just my view on quantum computers. I think quantum computers are a wonderful setting for experiments in the foundation of physics. I think they're many, many years away from doing anything useful besides cryptography, because the algorithms don't seem to be there yet, and the complexity is not there yet. But that's a different topic. So thank you very much. I hope you enjoyed it, and I hope it made sense.
Wonderful. Arik, thank you so much. That's absolutely wonderful. So incredibly in depth. Let me do this. If it's okay, let me stop your screen share.
Mm-hmm.
And then we have a few minutes for questions. And then I think at the top of the hour, we'll probably just do open discussion. So
Sure.
Let me see. I'll stop sharing there. Okay. And so let me see. Why don't I start with Jack this time? Because I started with Michael last time. Oh, Jack,
you're on
muted,
mute,
sir.
Yeah, thanks, Arik. That was fantastic. Yeah, no, I agree with you that retrocausal is more fundamental, because if you look at than the back action, because if you actually look at Sutherland's equation, his expression for back action involves the weak measurement, which you need the destiny. You know, yes, of course. I agree with that. Well, I have to. That's pretty interesting. I mean, you said things I wasn't aware of, but there's one thing I could tell you. There's this guy. Just as recently, the last couple of days, his name is Miles Albert, and he's sort of like Gary Nolan. He's a successful, I guess he's multimillionaire. One of the developers, pioneers in blockchain technologies up in San Francisco. And he is financing this company in Silicon Valley that's interfacing brain cells with inorganic like metamaterial stuff, and that I think that's going to get the back reaction. So I think we are going to definitely get conscious computers. I mean, but because we're going to be imitating at the micro level.
If we can actually imitate it at the micro level, and we understand.
Well, that's what he's doing.
Yeah.
There's a big development. It's a new thing. I think I sent you the link. It's called orgioids. So just look at that. It's like a, 50 different authors.
Mhm.
And this is it's a fairly new development.
Mhm.
And it's the kind of thing that Elon Musk, is trying to interface
Mhm.
with the
Yeah.
computer. It's that kind of stuff.
Mhm.
And I'm just learning about it myself. So I think that's the key. And I also think that that's the technology that's in the materials that
Mhm.
Larry Lemke was talking
Mhm.
about. So because I think those sources, whatever you want to call them, that they
Mhm.
are conscious artificial intelligence.
Mhm.
So
Mhm.
okay, so that's the only point I kind of disagreed
Mhm.
with your pessimistic conclusion.
It's
All
not
right.
pessimistic. I actually think it's optimistic because I'm not sure that I want a conscious computer. So
Well, I think it's coming whether you want it or not. All right. Okay, I'm done.
Okay.
Who's next?
Yeah. So let's go to Mr. Perrone, who has been patiently waiting with his hand up.
Thanks, Tim. So I have one quick question, hopefully, and one longer question. So one thing I've noticed is a lot of animal species we generally consider to be conscious at some level, they require sleep. So what's interesting about that is, like, if something doesn't sleep for a really long period of time, the physiological stress of maintaining whatever entangled state consciousness is, if it's that, seems to just overwhelm the biological system. So maybe that's a metric for determining which organisms are conscious in some sense, similar to how we are.
I believe that sleep per se is more of a wet-wear maintenance issue because of, I think that eventually the chemical composition of the brain, some of the glands just get tired of emitting whatever is required to keep you in an awake state. And sleep is required to recalibrate the various hormones that are required to keep us in shape. I personally don't think that consciousness per se is linked to sleep. I think it's got to do with how the brain works from a biological point of view.
Do organisms that only have ganglia require sleep?
Well, it's an interesting question. Ganglia, basically, like worms have ganglias, and all animals with a nervous system, which is more than a few neurons, have some ganglions to try and connect those nerves together. I don't know if snails sleep, so I can't answer that.
So maybe the upkeep on the wetware is less difficult. But I don't know. It's possible that once you reach a certain complexity level, there's also maintenance of some quantum states over.
It might be, yeah.
We know entangled states typically have a finite lifespan. So awake consciousness might be something like that. And the other question was, so and this is more of a physics thing. So does the non-unitarity we discussed relate to Wigner quasi-probability distributions if it breaks the Born rule, or are Wigner functions still unitary? I mean, this is more of a, I mean, maybe this is...
Jack should answer that.
Sure.
Can you hear me? No, it's non-unitary.
So Wigner functions are or not?
Well, no, Wigner functions are unitary, but the Wigner function is going to be modified in the presence of back reaction. It's not going to evolve the same way.
Cool. So the Wigner function.
It's good. I mean, I haven't done a calculation. I mean, that's something that requires like computer simulation. See what happens to the what happens to the wave functions when they have a source. That has to be computed. But I mean, there'll still be a Wigner probability distribution, but it's not going to evolve in a unitary way. It's going to have sources and sinks.
That's exciting.
That's exactly right. Because basically, as soon as you go into a non-equilibrium system, you're going into elements of things like non-causality. So it starts getting very interesting.
Yeah.
Excellent. And I have 3 more questions for you, Maurice, later on, if you're still around.
Yeah, sure. No problems.
Thank you. Anyone else?
One thing I would... Yeah, go for it.
I have a question about to Arik. Jack looks at the flight characteristics of UFOs and takes them as a starting point without considering anything. There is something called Valis, the idea of the future consciousness. And I had an experience with that, more than one, many experiences with it. And it always happens when one is asleep, when you're not actually using your sensory inputs. But I noticed during that time, I'm getting, it's like a shared cognitive environment where I'm getting much more cognitive space. I'm having much more, I'm not getting automatic input from my body. My sensory organs aren't working, even though I can feel body, but it's completely different. I'm actually, it's like instead of having the 2-lane highway, I have a super highway, and it's going back and forth, and I feel all my experiences and remember them, and they're creating a higher level of the consciousness we're talking about.
Well, you're describing something that feels a bit like the kind of experience that you'll have if you take mushrooms or something like that, where you break some of the barriers in your brain of time.
Yes. Well, one time when I took mushrooms, this was when I first met Jack 40 years ago. I was chewing some mushrooms, and he came over, and he walks over, and he looks at me, and I'm just chewing them, right? And I'm standing in the doorway of our new house. Jack has just moved in, and he looks at me accusingly, and he goes, "Are you on psychedelics?" And I was so annoyed that I wasn't high at all, but he had somehow guessed it. And I said, "No, I'm not. How dare you?" And I'm thinking, how did he guess this? And you know what?
My guess is David.
But wait,
my guess is okay. Sorry.
And let me just say that Jack, I never did get high. I ate those mushrooms, but Jack got high and was high for the whole night on mushrooms on my trip that I never had. And that was something that I've never forgotten. This was 40 years ago, this year.
Teleportation.
But I did want to ask one more thing, was in my experiences are similar to what Ingo Swann talked about, psychic penetration, because it's not like I'm alive and in a room awake and imagining something like with Russell Targ, but instead I'm completely asleep and I'm often in another body. And it feels like my body. It doesn't feel any different, but I can see myself in a mirror and I'm not in the same body. And that's when I go back to the past, when I, was actually in the past, feels like I'm in the past. I'm in another person's body. I'm not in my own body. I'm dressed in different clothes. And that is something that
the military has, they have soldiers who do that. According to Russell Targ, they have psychic core. Well, according to Uri Geller too, they apparently Geller says the Mossad has that.
Wow.
I guess from my perspective, I can have two comments. The first comment is that it's very possible that when you do take mushrooms, it changed something about the structure of your brain, and so the barrier between your sleep life and your memory is not as strong, so you can experience a lot of things concurrently. And regarding those other experiences, I ended my talk by saying that I believe that this spark of consciousness is something that comes from the screen, and behind the screen there's everything, and it's very possible that other things come in when you sleep.
But how could Jack take that quantum experience from me?
No, that's easy. That's easy to conceptually understand in a qualitative way. It's teleportation, but with entanglement signaling. So that's once you have that, you could do all these. But let's not spend a lot of time on that right now.
There's
another possibility.
That was the 70s, right? So
there's another possibility that's not being addressed.
No,
and
that's nothing to do with the 70s. I don't think.
Let go ahead.
Any other questions?
Yeah. Can you hear me?
Yeah.
This is Cortona, Walt Williams. There's another possibility, David, in I hate to bring it up because people don't really know very much about the subject, especially the scientific community. And it's called the Kabbalah. In the Kabbalah, it describes 4 states of consciousness. And one of them is called Yetzirah, which is Hebrew for the Sanskrit word astral plane. And that's where the psychic state takes place, is in theta rhythm. And Monroe did a lot of stuff in this area as well, with hemisync. I experimented with it quite a bit myself. It's like taking an acid trip, only you can do it with electrical frequencies. You put these signals into your head to entrain the brain into theta rhythm, and you start having psychic experiences. Well, it turns out that's part of the reason why I was studying the psychics with relationship to alien contact, is because all the psychics can see the alien craft. But it can be, I've been with people with cameras set up, and they're pointing and say, see the craft right there, and the guy standing next to them can't see it. How's that happening? Well, it turns out that the guy that's seeing the craft, his consciousness is up in Yetzirah. He's seeing in the astral plane. And that's where the alien craft are operating, is up in the astral plane. That's a guess on my part. It's speculative, but it's convenient. If the aliens are truly using super consciousness in their hardware, meaning psionic machines, it's higher than the physical plane, which is the ASEA. It's above radar. They can't detect it with radar. You can't detect it with radio waves. Magnetometers don't detect it. Yet the craft are still seeable by people who are psychics. I mean, it's very convenient.
That's because but we understand that in principle. That's because the pilot waves, the quantum waves, are physical waves. So that's an alternative communication channel to electromagnetic waves. So the astral plane is actually controlled. It's it's entangled Bohmian
right.
waves. But we're able to.
And then there's
shared cognitive environment. That's what I think.
That's exactly the point. That's exactly the point.
I agree.
Well, if it's okay,
but I didn't see any UFO.
I still have a couple of hands raised. I have Thorborn McBain. I think he's there.
Yes, I
remember. There we go. Can you enable your camera, sir?
Yeah.
The camera.
And welcome back.
Yeah, the camera isn't working. So
okay.
To suffice with that video. I guess I have 2 things for what Arik was just talking about. One of them kind of ties into what else was just brought up for sleep. So for most neuroscientists, and even starting in the 70s with psychologists, their concept of consciousness has to do with internal modeling. And so they have the entire field of cognitive science that spun up out of that concept. And that ties into sleep. And what Michael was saying is that what we know is that the majority of sleep is some type of recompiling of our internal models. And there's a ton of interesting psychophysical literature that they use to explore how we internally model reality. And so that if you imagine 2 chiral structures, if you can envision this in your head, they would rotate them in space in 3 dimensions and then ask and have a presentation of 2 of them. And they would ask people, are these the same object or are they different objects, right? It could be like a molecule or anything like that. And linearly with the rotation distance, right? It takes the time it takes for someone to recognize it or determine if it's not the same is 100% linear with the rotation angle. So the farther it's rotated, the longer it takes for them to solve the problem of whether it's the same structure. And what they ended up looking at later on in studying it is that people literally have a model of it in their head and they rotate the structure in their head, right? The representation of it. And so a ton of the question of sentience, if we're just talking about something sensing the environment versus modeling it, that's kind of one of the discriminating factors is does an entity have the ability to model the environment? And this is the issue if you're worried about ChatGPT or nonsense like that. It's a large language model, but it doesn't model reality. And so it's a language game that people are playing Bayesian statistics with, and it spits out data, but it doesn't have any internal models of reality. So part of what I'm saying with the sleep thing is it's interesting that that was brought up because that is a strong indicator that an entity has some sort of reorganizing routine for its internal models. One. The second thing that I wanted to get into is when you were talking about quantum computers and the ramifications of that, per a little bit of what I was saying yesterday, the issue that we're at with technology at this point, especially with a lot of the technology being a cognitive prosthetic. So the computers that we're using now are cognitive prosthetics. We're all meeting across the globe. As we increase the technology, our cognitive power increases in ways that we're currently not measuring effectively. There's some people trying to look at this, right? And so what I always argue is that we're dealing with a limit here, a mathematical limit, not like a ceiling. And you can't look, if you try to look 100 years in the future, we won't understand what sort of cognitive augmentative effects some of these tools will have on us. And so it's more likely the case that some 13-year-old kid is going to have a quantum computer embedded in his head, and he's going to be building a flying skateboard and giving us the middle finger, than it is the case that there's going to be robots that want to kill us, right? And so we're not thinking about this appropriately because we're not thinking about all these tools as cognitive prostheses too. And so it's easy to like fall into fear porn over some of that stuff. But the one thing I'd ask is, look at the number one, the fact that our brain integrates these tools into our cognitive model, our internal model of the state of the world. We model these things as being extensions of ourselves. So again, if I'm like an alien looking at people and a person gets in a car, that car is an extension of that person. And then we're playing an ontological game, and I could ontologically argue that that car is part of that person, right? And this is the dilemma with technology, is it's easy for us. We feel like we're individual people and we can disassociate it ontologically and say, I'm a person, this computer I'm talking to you guys with isn't a part of me. But the problem is it is a part of me. And so that's one thing I'd say as a caveat and food for thought when people are thinking about future technology, is it interleaves with our capability itself. And so it's not going to be a caveman fighting a quantum computer robot, right? It's more likely the case that we're winding up in some Ray Kurzweil type situation where we merge with it.
And I think Ray Kurzweil does have it right, because I think he is talking about enhancement as opposed to separation.
Exactly, yeah, and I think that's the trend that we've been seeing, and so it'd be more of like a bifurcation event for that not to happen.
Yeah. Well,
You know,
thanks, James. Yeah. Sorry.
Thor said something that was really interesting. Yesterday, he was talking about the technologies that were developed in other areas and that were used. And then Maurice was using that formula before, and he was saying how that came up having to do with computing casualties in war, and that is ending up using it for consciousness. And I thought that's exactly what Thor, is that your name? Thor or Thorbjorn?
Yeah, Thorbjorn, yeah. Actually,
Thorbjorn. I'm in Norway, so we have Thorbjorn all the time.
It's Danish, so it's Thor instead of Tor. But
okay.
One other point I'd say about the LSD, when you guys were talking about psychotropics, is they're very, very well studied from a neuroscience perspective. There's a lot we don't know about the brain. And the thing to understand about them is what they are is they're modulators of modulators. And so dopamine, we have a dopamine system in our brain. I'm sure everyone's heard of dopamine. And the dopamine system basically innervates all of these portions of our brain, and it modulates the activity. So dopamine modulates, for example, your prefrontal cortex. And that modulation, if you turn it off in some sense, that's how you wind up with schizophrenia, and every single pattern looks real to you, right? You see connections everywhere. And so it's a fine line.
That's the same with autism as well.
Autism is an overgrowth of connection.
Autism is different, but
autism is not even a well-defined. It's not even. It's not. Autism is clinical psychologists trying to play with things that they don't like. They don't like a person, or they don't like how they talk or behave, and so they say it's a clinical defect. They
actually took it off. They took it off from the spec. They used to define it on the spectrum. They actually took off the whole category completely.
Yeah, there's no biomarkers for it. So my point is there are biomarkers for schizophrenia. there
I
aren't.
just want to make one comment about what David said, and essentially what I'm actually saying is that there's an underlying mathematics that links all of these subject matters. So, for example, if you look at, for example, axiomatic dimensional analysis, you can assign that. So this is part of complexity mathematics, which links into the feedback structure in Sutherland's retrocausality. It feeds back into the two-way interaction between a particle and a wave function. It feeds into the fact that you're looking at a Bohmian or de Broglie type quantum mechanical perspective. It's all the same stuff. So what you have to do is you have to go back to the root of the quantum mechanical issue, the framework, and slowly build yourself up, and to start to look how that framework impacts itself on different aspects of what we're looking at. So we're now going from a Bohmian type standard mechanism that was around in the 1950s. We're extending it into a relativistic aspect. So we're looking at, for example, what Sutherland did was therefore, and all of this flows in a sequential manner in the way that we then start looking at both typical and atypical phenomena. In other words, why is it that if you've got a rock on a beach, it doesn't jump up? Why doesn't it jump up? Because if I'm sitting there on the beach and staring at it, I'll have to wait longer than the age of the universe to see it jump up, right? So typicality. But on the other hand, we're seeing things which are atypical. The universe is atypical. It's an open system. So somehow we've got to combine all this stuff into a formulistic, sensible, mathematical formalism which has an audit trail. And so consequently,
Maurice,
if you understand the principle,
I
you
agree with you,
understand
but
everything.
I think though that there's a challenge in it, because I used to do some work many years ago about protein folding. I think to try and explain protein folding by understanding orbital structure of hydrogens is not a useful way. So you can have the best understanding of a system at a certain level, but not everything flows linearly from an understanding of a certain level.
I'd have to disagree because basically what you have is you have a scaling schemata. So when you have hierarchies, as you put on your slide, the hierarchies are defined by the scaling aspects. That's how you link classical mechanics to quantum mechanics. End of.
There are different type of emergence, and not all emergence, according to lots of people, can be defined just in terms of the constituents. Sometimes some emergence, we call it radical emergence, can't always be explained through the constituents. So I'm not an expert in it.
Exogenous behavior. So,
gentlemen, if I could jump in
for... I've seen this before, is that if you have a system which is constructed by internal factors, this is where self-organized criticality came into being, is that Peer Back, when he wrote his book on how nature works, he was looking at self-organized natural systems. So they're internal. There's no open. It's not really an open system. And then later in time, they realized that these systems were tuned. How are they tuned? From the outside. So they're open systems. So you have to understand the mathematics before you start making, in a sense, stories up that that don't have any kind of, the bottom line is that you're taking the data and you're constructing a mathematical model. If the mathematical model matches the data, fantastic, it's a good model, until more data comes along or you get a better model.
Absolutely, the correct level, you're absolutely right, as long as we understand the level that we want to do it at.
Gentlemen, if I could jump in for just a moment. John Ramirez had a question, and then perhaps we could go to open discussion after that, because it seems like we're just about there. So, John, would you like to go, sir?
Sure. Thanks, Tim. Thank you very much, Erica. It's a fascinating briefing that you provided. My question has an answer that all of us will get the answer to eventually, because all of us will die. And that I can predict the future, all of us will die. My question is, does consciousness survive the death and deterioration of the wetware?
That's a view. My view is that consciousness doesn't survive as an entity with an individual identity, but it comes back into the soup of global consciousness. But on the other hand, I'm also personally, and through lots of things, I've seen a lot of accounts of reincarnation. So some identity does come through, but I'm not sure there's a continuity of individual identity, but I think there's a continuity of a global identity, if you want to call it that way.
Are we, should I?
Yes, we're back.
Okay, let me say something about that. Well, okay, it's funny. I was just thinking about that last night. Some of this reincarnation could happen from kind of epigenetics that memories are actually encoded at the DNA level and they are transmitted, to future generations. That would certainly have an evolutionary advantage, just like retrocausality. As a dome, and there are plenty of cases like that, like in India, this little girl, we all know there are studies in reincarnation. Some of them are quite extraordinary, And the other thing, in terms of survival of our personal, we have like Avatar, the PK Dick, I forget the name of the story, but they made it the movie Transcendence, which is Johnny Depp. That's quite possible in terms of post-quantum picture. If the pilot waves are physically real as they are in the Bohmian interpretation, in principle, you can upload the memories into a computer and then download it, say, into a clone body of yourself, and you might be able to get a kind of immortality that way.
By the way, according to the model that I presented, if you can completely replicate your biological pattern in your brain, you can get that kind of immortality because your identity is going to come from that.
Yes, that's what I said. That's what I meant.
Yeah.
That's exactly what I meant.
One thing I've always wondered about, though, Jack, is if you can do that with a machine, but you also have this global consciousness that Arik was talking about.
That too.
The pilot waves, it just exists in that global consciousness and then go into other brains in future generations. Maybe the global consciousness recycles the same pilot wave information patterns to kind of create different people.
Yes.
So.
I think there's something to that, and that gets now to the holographic picture. The Lenny Susskind, Gerard de Hoopt holograph, and the idea is that we have the dark energy that's accelerating the expansion of the universe. We have what's called a future. It's the de Sitter future cosmological event horizon, which what's the guy, Seth Lloyd, MIT, has this paper in Scientific American. The black hole horizon is the most world's efficient computer. Well, our future horizon is also like a post-quantum computer, and you could say it's EPR. In the holographic picture, EPR equals ER. It's the quantum entanglement on this future horizon, which is kind of like the conscious mind, if you want to say, the conscious mind of God. And we are holographic images, but projected by these Aharonov destiny, destiny waves coming back. That's the local causality being the most fundamental.
Sorry, did you guys want me to still moderate with hands up, or are we doing open discussion now?
Let's just go with open.
I think we should do a bit of open discussion.
Okay.
I need to go in about 5 minutes.
Just try and jump in, perhaps, if you can, Michael and Thorborn.
Okay,
sure.
So I have a point that someone asked something about autism, and the fact of the matter is we've actually done. It's number one. It's, I said, like a clinical definition. It's not really a neuroscientific thing, and then it's potentially a couple of phenomena combined into one. But the best biomarker that we have right now for it is actually testosterone exposure to the brain.
What? So that's what exposure? What?
Testosterone. especially
too much or too little?
testosterone, too much, and in developing children. And that ties into what Michael was mentioning in the chat yesterday with endocrine disruptors. And then I was a little bit, didn't get to finish on the part of talking about LSD or psychotropics. And it's interesting, David, that you mentioned mushrooms. And I would posit this as something for everyone to look into if you're interested in this phenomenon. The first thing I'll say is I'm really very skeptical. I only believe things that I see, but I've also seen plenty of things that don't make any sense to me. So I leave plenty of room for realizing that I don't understand what's going on oftentimes. But the one thing that I'd say in particular with mushrooms is the majority of the people that I've observed that report ESP type phenomena have a chronic fungal infection. And so it's also likely the case that the lysergic acid or any of these psychotropic substances aren't the only thing that's going on in the brain of someone who has something happening, right? The next thing that I point out is someone also, I think, David, you mentioned Vallis. It's a PKD book, Philip K. Dick.
Yes.
The point that I would mention in Vallis is he posits like there's these satellites beaming energy into people's heads, and that's what's killing them or giving them cancer. The point of me mentioning mushrooms is if you're interested in looking at consciousness or other phenomena, I'd suggest that you consider looking at how mycelium work, because they look like dendritic networks. And the one
That's
thing that I
right.
would say is if we're dealing with contact, potentially alien contact or anything else, I'd say it's likely the case that they may operate on a time frequency that we don't understand. Or like Jack was mentioning, that there's a time element that we don't understand. And so the ability for us to see what's happening at a different scale with things like, and I'm sure you guys have seen the fungal networks where they use them to draw roadmaps and stuff. There's likely the case that there's other sorts of types of consciousness that we're not basically prepared theoretically.
How about jellyfish? You know, Arik, I wanted to ask you about jellyfish because
So I'm
remember
going to mention
about
that. I just want to also respond to you, Michael. Actually, I didn't have time to discuss it. I mentioned briefly this book, The Secret Life of Trees, because it's my first introduction to mycelium networks. And it's actually an insight that I had, and I shared it with some people, that we get confused when we think about consciousness, we get confused about speed and time scale. And if we were really to accelerate our time scale, then we'll think, oh, forests are conscious. But I alluded to it in my slide about evolution. I do think actually the consciousness occurs also in, for example, for forests and trees. I just think that it's a group consciousness, it's a morphic consciousness, while individual consciousness, I think, arises through that mechanism that we describe. So I believe personally that
his robots, little Corey.
Oh, sorry, you're not muted, Platonus.
What happened?
Oh, wait, I think he was reading something online, but
No, I think Arik lost his connection or something.
Is
okay.
Arik there?
No, he's
He's
not here.
Sorry,
back.
no,
He's back.
No, I'm back. My connection was,
Yeah.
Sorry, I'm back. Yeah. I just want to make the point that I agree with you completely, and I kind of make me think when you mentioned about fungal infections and ESP, maybe it's just like maybe fungus actually do have a much stronger role in our life than we are aware of as any other parasites that we picked up over the years, and we don't really know what they do to us.
Thor, are you talking about like fungal nail infections? Could that be it too? Would that be?
No,
Why
so
not?
so the problem with fungus, as everyone knows, is that fungus isn't a mushroom. A mushroom is like a flag for the organism, right? And so by the time you have a fungal nail infection, it means your entire body is infected. And it's inside your body everywhere. And so there's huge, again, like I'm saying, we just really don't understand it. I even have a hypothesis, and I've delved into this some with some microbiologists who I know. I really don't believe that, I have somewhat of a belief that fungi don't originate from Earth, that they're like an extraterrestrial, they came in on an asteroid. And it could be the case that bacteria did. But what I'm saying is their behavior from an animal diversity perspective is so bizarre and so different. It's like you said, you may see a mushroom, you may see fungus on your toes. If you see fungus on your toes, it's in your brain, just so you know. And there's a ton going on there that we don't know, and I'm just saying it's worth looking into and understanding, especially if we're talking about.
If I could interject, Thor, I have heard, and I didn't follow up on this, but I have heard about underground fungal networks actually having
Right, yes.
communications.
Exactly. Yep. Electronic communications like neurons.
Yeah. And even the forest system too. The forests have that. The roots of the trees. That's, I guess that's what Arik was referring to. That, that the forests have a kind of collective consciousness. This whole Gaia thing is, there's something to it.
The most complex biological system is in the soil. It's far more complex and intertwined with all these things, the roots, the fungi, the organisms. It's far more intertwined and complicated than what's above the ground or what's in the sea.
Yeah, who's talking? Who's that?
Creon. Creon.
Well, that's Creon? Oh, okay.
Yeah.
Guys, I apologize. I need to go. I'm going to have to bid you farewell, and thank you very much for the opportunity.
All right. By the way, how's the conference? How's the conference with Hammeroff? How is it down there in Sicily? Are you still in Sicily?
It's the most beautiful place. It's a nice conference. Great people, and some of the philosophers are a bit out there, but all the rest are great.
I have one important question for Arik.
Mm-hmm.
Quick, go ahead.
What is that French recipe for the scallops?
It's really easy. You open the scallops, you take a knife, you cut them up on the top of it, and you just squeeze a few drops of lemon, and you eat them like that.
Oh,
okay. Well, thank you.
I don't think I'll ever eat another scallop.
Okay. Well, I have another important question for Jack.
Okay. Thank you. Bye-bye.
Okay.
Thank you
See
very
ya.
much.
Bye,
Eric.
Arik.
This sort of gets back to that question of the whole thing about, does consciousness survive bodily death and so forth. I think there's sort of two generic sort of ways of looking at consciousness. One is that it's an epiphenomenon of the physical wetware, right? And the other is that it's a field, or a field that's being broadcast, and the wetware are basically receivers of it, right? And if you take the first view, that it's basically an epiphenomenon that emerges from the bottom up, then obviously if the wetware goes away, then consciousness goes away. Conversely, if you look upon it as a field that's radiated out and we are receivers of that field, then that's a different story. So my question, Jack, I guess, is in this whole retrocausality being essential for, and the feedback being essential for consciousness, is there anything in the theory that discriminates between
No,
those?
I think both are both. It's not one or the other. It's both. It can be both.
Okay.
I mean, there's there are effects because it's even from the weak measurement point of view. There's the advanced destiny waves and the past history waves, but both the wetware and the well, let's put it this way: if we're holographic projections from the future horizon, then the wetware is also a holographic projection. So, and that's all retrocausal. I mean, it's both retrocausal and destiny and history. The way you just look at Sutherland's mathematics, it's all pretty clear. The weak measurement.
Here's another question I would pose. This whole question of the retrocausality phenomenon. I personally have experienced it in my own life a few times, and when it does occur, it's very powerful, kind of you can't question it. But particularly from a just a personal perspective, it doesn't appear to occur all the time.
No, that's different scales. It's on the small scale, it's happening all the time. Otherwise, we wouldn't be here.
Right.
the quantum weak measurement is part of the fabric of the universe.
But when you get into these retrocausal loops, like, getting the phone call in 1953 that then sets you on the course that, 50 years in the future allows you to,
Yes.
Why does that happen sometimes and not all the time? In other words,
Well, I don't know, but the point
I
is,
mean, to me, that's the question: is there somebody able to engineer that
oh yeah, that's
at a higher
technology.
level, right?
Oh, sure, it's technology. It's definitely technology, right? They're manipulating. I mean, I don't claim to know everything about, I mean, all I claim is that I have a general qualitative understanding how these things, do not violate the laws
Well,
of nature.
I guess the point I started getting at is if it is possible that these retrocausal loops, where the causality is not actually clear, which direction it's going, if it's possible to have them at the macro scale sometimes, but not others, then that sort of implies that there's a choice involved in that, right? That somebody.
Yeah, no, I think the macroscope that, these dramatic events like my phone calls and people's, like that, these Valis-like events, those are engineered. Definitely engineered,
like Joan of Arc, right? Joan of Arc is one of the,
Yeah. Or let me get, okay.
But I guess my point is, if it's possible for somebody who's, smarter than I am to engineer those, then that would seem to imply that that the universe is not entirely deterministic. Otherwise, there'd be no degrees of freedom available to engineer that.
Well, I don't know what you mean by deterministic, but I think the universe is, the universe is conscious in the same way we are. That's part of the math.
But the point is, if I could come in, as some super intelligence, and engineer, the retrocausal loop that you experience,
yes,
or not,
yes,
then there has to have been some degree of discretion involved in that. In other words, if I could do it or not do it, then the fact that existed by itself is not deterministic.
Well, okay. Well, so what? I don't care about determinism. I'm willing to give up.
Well, I mean, I do. I mean, I'm trying to figure out is this when you say that there's a back from the future, component.
Let me give an example. Let me give a concrete example. Okay, concrete example. You tell me how. Very concrete example. I get the damn phone calls in 1953, right? They say it says I'm going to meet the others in 20 years, right? Okay, 20 years go by. And I've sort of forgotten about it, right? 20 years go by, but this guy, I'm living with Fred Wolf. This guy, Bob Tobin, comes down from Chicago, an old friend of Fred Wolf from high school. And suddenly he tells me and Fred, oh, there's this guy, Uri Geller, and he's able to bend metal with his mind. We never heard, we were just very straight.
I was in Berkeley at the same time. I remember that.
Yeah, okay. But he comes down and Bob says, listen, I got all this money. I want you guys to try to explain with quantum mechanics how consciousness works, how Uri Geller could bend metal. And I got money to pay you to do it. Okay.
Yeah.
Now wait, this is Christmas time. Christmas time, 1970. When was it? 1973. Christmas time comes down. All right. Shortly after Bob goes back to Chicago, Fred gets two calls. Gets a call from John Hasted at Birkbeck College and of this French guy from the University of Paris. Said, take your sabbatical. We have two academic appointments. You commute between Paris and London, okay, and teach these courses in atomic physics at Birkbeck, where David Bohm is, where I used to be. At the same, within a few days after that, Abdus Salam calls me from Imperial College. He's the head of theoretical physics, Imperial College. I had met him when I was at Harwell Atomic Energy, gone down to Imperial College and met him. So he knew me, and he invites me to go to Trieste because he likes what I'm doing on these little black hole models of hadrons and stuff like that, similar to what he's doing. So suddenly, so we're on our way to Europe. Before I'm about to go to London and then to Trieste, and for Salam, but before I'm with my girlfriend with her her mother-in-law lives in Carmel Valley. Now get this. Now this is the weird. Now we're getting to the spooky part that I'm going to say is proof of time travel. Okay, proof of engineered loops in time. I'm in bed. It's Sunday. I'm supposed to fly out on Wednesday. Sunday morning in Carmel Valley. I'm in bed. Sharon's mother brings in the San Francisco Chronicle. I open up the magazine, the San Francisco Chronicle. There's a big spread, color spread on Stanford Research Institute investigations of Uri Geller and Pat Price, all these remote viewing, da da da. So, hey, this is just exactly what Bob Tobin is giving us money, you know, it's when we're in Europe to also work on this, right? So Monday morning, early Monday morning comes, I pick up the phone, so I better call Stanford Research Institute, okay? I call, I get through Brendan O'Regan, who's picks up the phone. He's this is all CIA now, right? Brendan, who's the right-hand man of Edgar Mitchell, the astronaut Edgar Mitchell, okay? And I picked the phone, he says, Dr. Sarfatti, we were hoping you would call us. Dr. Sarfatti, okay, now how is that, how are they, I mean, yeah, I'm in my girlfriend's mother's house in Carmel Valley. She hands me the newspapers, the San Francisco Chronicle. I mean, that has to be engineered from, and it's exactly 20 years, is exactly 20 years after the phone call. And then, okay, so I drive up there. I meet Brendan at SRI. He takes it right away. Who's the first guy I meet is Edgar Mitchell at the Institute of Noetic Science. Their office is right across from SRI and Edgar Mitchell. And then there's this whole thing where I'm there for 17 hours. And you could hear the tape recording. Somebody actually, Sol Paul Sirag said, as part of the tape recording, you hear me. It's online. I put it online. It's only like an hour, but it was really like 4 or 5 hours. Only one segment. So apparently the CIA has the full recording. Everything was recorded. Jacques Vallée was the guy who arranged this. He was supposed to be there, but he didn't show up. Here's Jacques Vallée, right? He didn't show up, but he apparently arranged it. And you can hear me talking, my first encounter with Hal Puthoff and Russell Targ and Dean Brown, all these other, Brendan O'Regan, and you'll hear Russell start talking about this rabbi, I forget the name of the rabbi, this Kabbalistic rabbi who's saying the flying saucers are coming back from the future. I didn't say it. This is Russell Targ talking about it. And then I said, I remember. and you hear me telling the story about the phone call that I got in 13 and saying it was a conscious computer on board. You hear me talking in 1973, you hear, and then you hear Brendan and his, I don't know if you ever knew Brendan. He's Irish, kind of like a magician, sort of, very mischievous, elfy like, like a leprechaun kind of. And you'll hear Brendan say, oh yeah, we have a couple of hundred incidents like that. And plus, remember the computer said, we have contacted several hundred young minds. And Brendan confirms all that. Now, whether they're playing, so there's no way to explain this without it being literally true. And now, of course, up until December of 2017, when the Leslie Kean Blumenthal article came out, right? But it was late October in 2017. I'm at the Bohm Centennial. Arik was there, and who did I run into? I run into Kit Green and Hal Puthoff, right? So I'm hanging out with them, and I'm in their hotel room after this Fetzer Foundation Bohm thing, and they're running out of the room all the time because they're calling for Langley's calling them, and I guess the New York Times. They're helping to set up the New York Times article on the Pentagon release of the UFO, and I'm right there in the room, right? So this is all like so weird, okay? So the point is, what I'm also trying to say, the reason now I'm pushing so hard that my 19th, then there's the thing that I only remembered one phone call. My mother remembers weeks of phone calls. There's missing time. Sounds like an abduction thing. Who the hell knows what's happening? But basically what I'm saying now, and it normally would sound crazy, except now it's not crazy anymore. We have John Ramirez who's having, and Jem Simivan. And so the point is, I said there's abundant anecdotal folkloric evidence of this destiny effect, that these
Right.
higher intelligence from the future is doing exactly what,
If I could jump in, I have
Go
to
ahead.
leave. I've got another
ahead.
meeting at 4 here. So
Go ahead.
I think I missed Maurice. I don't know if he's in there anymore, but I can email him after. But I guess for anyone watching online later, these might be helpful. When he was describing non-equilibrium states, is it generally possible to describe a non-equilibrium state as a equilibrium state with a different effective potential? So
well,
like without a
to
forcing
some
term.
extent, well, yeah, in fact, I do that as an approximation. There's like an effective non-equilibrium temperature, which depends upon the power flux, the like the Poynting vector, the energy density per unit area. One way of looking at it, and I think it's just an approximate. It's like a perturbation expansion sort of thing, like a Taylor series. It's not. It's just a model. But if you have bosons, if it's a boson system, what happens is the effective temperature in the effective local temperature in the non-equilibrium system is going down because you have energy flowing with like order. It's lowering the entropy. So it's like the effective temperature is going down, and then it goes below the equilibrium temperature for Bose-Einstein condensation. So that's how I can get a room temperature superconductor in this non-equilibrium case, because there is like an effective local non-equilibrium temperature, which is actually lower than the ambient equilibrium temperature of the environment. So the answer is yes. We try to model the non-equilibrium system as a kind of equilibrium system, but with a different temperature. Okay.
So and the analogy for people online, I guess there's a few videos online now of if you have some magnets spinning on a Dremel, you can actually levitate another magnet at a distance from the first magnet because of the drag of the air resistance on the first. There's a phase shift between them, and then the saddle node that normally the saddle node potential between the magnets that normally exists is stabilized by the rotation of the thing, so you get an effective parabolic potential or whatever it is.
Well, that may be, but why are you bringing that up? Yeah, that's interesting.
I mean, just for anyone future reference, it's an example of non-equilibrium system where the oscillation produces a new potential well where stuff can come trap.
Yeah. Oh yeah, yeah. But it's not a mechanism for flying source of propulsion, though.
Oh no, yeah, just an example case. But so, and then for the atypical behavior he discussed, let's see, what was I saying here? Yeah, actually, this is a good one too. So when we assume that the atypical behaviors have parametric constants that vary with external effects, when is that a valid assumption, and when is it not separable from some other system that's external?
I don't know. You're asking these details. You have to ask him, because I'm not.
Yeah, I'll email him about that later.
Yeah.
And the other one, maybe you might have
a good question, but it's.
I'll ask him about it. So as for maybe this one's one for him too, but I was wondering to ask, how does self-organized criticality relate to hyperbolic heat and diffusion equations? Maybe that's one for him. Yeah.
Well, Michael, I think you had one for Larry, right? As well.
Did I think I may have asked that one already for Larry.
Okay. I just wanted.
Yeah, I was just bringing up the borophene and stuff, and we'll.
So Michael, where are you? Where are you physically? Where
Massachusetts.
Are you? Okay, and what are you? What are you, a student? What is your situation?
Graduate from WPI. Got my own startup. We do material science consulting.
Okay. Oh, you're that. Okay.
Where in Massachusetts?
Worcester.
Oh, that's right. Worcester. Okay, I remember.
Worcester,
Okay, I remember.
Western Massachusetts.
Okay. All right.
Oh,
good.
one that you might actually, you may have an answer to this one. So with the Prigogine effect, entropy increase is minimized, but can that entropy increase ever go negative? And is that just for the local system, or is that for the global
Not just
system?
the local system. the
Yeah,
local
I
system.
figured. All right. So yeah.
Read Prigogine it talks about this, and also there's Harold Morowitz. I don't know if he's still alive, from Yale. He's the guy who started talking about the neg entropy flows through non-equilibrium systems and how that lowers the effective entropy. And as you're lowering the entropy, it's effectively the temperature is going down too, right? Because what 1 over temperature is the partial derivative of the entropy with respect to the internal energy, and all that kind of stuff. So
Cool. And then based on that question, there was one additional concept here. So, I mean, with the Schrodinger equation, it's just a heat equation with a potential term added.
well, with imaginary time.
Yeah,
Or
right.
the other way around. The other way around.
Oh,
No.
right.
Okay. Diffusion
So-
equation that you get from the diffusion equation to the Schrodinger equation by changing the sign, putting an I in front of the time.
Right, yeah.
Yeah, the Schrodinger equation
For
has
the wave
imaginary-
equation, not for the probability distribution necessarily. Yeah.
it's a diffusion equation.
Yeah, so we're looking at I don't know if you're familiar with Daniel Sheehan's work, but we're getting some
Yeah,
promising
of course. I
results with
know
that.
Danny Sheehan. I know.
Oh,
Are you
excellent,
working-
excellent. So yeah, we're trying to replicate his results recently, and it's looking like you can produce macroscopic diffusion equations with an additional potential term that stabilize 2 different phases in a system, and then you can use that to produce energy from thermal fluctuations. But this seems different. This seems different from Prigogine's thing, maybe.
Oh yeah, no, I don't think it's. Yeah, it may not be the same. Well, I mean,
All
do you
right.
have an energy? Do you have? Are you pumping energy through the system?
So what I've found is a lot of these systems work with static energy. I mean, some are variable in time, but for example, Paul Tibato's graphene energy harvester, it works when there's an electrostatic charge on the graphene flake. Are you familiar with Paul Tibato's work?
No, I haven't been following this.
Oh,
Do me a
all right.
favor, would you send me some of these papers when you get a chance? I mean, I'm pretty
Excellent.
busy.
Yeah, because this I think goes beyond the Prigogine effect. We're getting like
It's Prigogine, but it's Prigogine.
sorry, yes, Prigogine. I've only been reading it, so I should, yeah. Anyway, Prigogine, yeah. So this seems to be going to something that's neg entropy potentially within you're producing an attractor state in a closed box, which appears to be minimizing the Poincare recurrence time.
But effectively, this
we'll
is
talk
like
about-
Maxwell's demon, right? I mean,
Maxwell's zombie is what Dan Sheehan and Remy Cornwall were calling it.
okay, so it's like rectifying
not
Brownian
intelligent.
motion.
Yeah, I mean, it would if true, it decouples information and energy being the same identically thing. It would there's a congruence there still, but there's something else going on here. The thermodynamic temperature and the fundamental kinetic energy are slightly different quantities. We call both energy, but it's not quite the same thing, maybe.
Okay, well, listen, I like to see the papers. Okay.
Sure. Yeah, I'll make a note to send you some. I got to leave for that other meeting.
Yeah, and thank you again, Michael. So, Jack, we're almost at the top of the next hour. Should we wrap things up for today, or
Well, no. Does anybody want to say anything? I don't know. I'm tired, but if somebody wants,
We're having a good discussion about spoon bending and metal rod bending in the chat. So,
I see that in chat. I see that in chat.
if anyone wants to comment by voice.
Yeah.
There was something I'd like to make a comment about if I could.
Go ahead.
Hi, Jack, and everybody. Yeah, when I was when Arik was talking about the brain modeling, and I only bring this up because I bumped into this guy. I don't know very much about it myself. It's not my field of expertise, but there's a fellow named Ron Blue, and he was a psychocyberneticist who engineered little quantum robots that he called Little Corey and Little Ricky. And his stuff was all over the internet at one time. It's all disappeared off the net. He died of a heart attack a couple of years ago. What he did is he studied how the brain works from an EKG perspective, and he modeled it using wavelet transforms. And then he hired a PhD in electrical engineering, and the two of them together used Brian Josephson JFETs. They reverse biased it, pull the band gap apart. And he wouldn't go into a lot of details about how they built this, because they sold the technology to a company who then went out of business, and the technology basically disappeared. It's under some kind of a patent arrangement. I think it was done.
Black? You mean it went black?
It went black. Exactly. That's exactly right.
But wait a minute. Well, you said Josephson things, but how do they get the low temperature to operate the Josephson junctions?
I said, I don't know how he did it. He didn't go into those details, but his robots run off of 9-volt batteries and give you an idea of the power density involved. You know, we're talking about smoke detector batteries.
Yes.
They do not use stored instruction sets. It's not CPU based. They're analog. And he claims that it works on something about they call the interference patterns of the wavelet transform between the quasi-oppositional processing of the opponent hemispheres.
It's like imitating the brain. It's like imitating.
Yeah, it's imitating the brain. I interviewed him. I have the tape somewhere where we talked about the difference between what the military is doing with the, the silicon cortex technology, that, the Texas Instrument devices that went back in the 1986, 87.
But just let me interject before, I don't want to lose that thought for a minute. The guy who was funding the research when I was a kid, the military research that sent me to Cornell, was one of the founders of Texas Instruments, Eugene McDermott.
Wow, cool.
He was in the OSS. He was involved with Wild Bill Donovan during World War II, and Phil Corsa. All these guys, they all knew each other. Yeah, it's all
interesting story about how they got started too. I mean, of how TI got started.
Okay, can you put those videos on the web?
It's the videos of his robots are on YouTube. And
can you send the links, please?
I will try to look it up. His website has disappeared, unfortunately, and most of his papers have disappeared. He was all over the place, and basically he was talking about, when Arik was talking about the number of bits and about the quantum loop. Basically, they're talking about the quantum loop.
Yeah.
Ron said the problem with his robots. I'm sorry.
Go ahead.
60 bits per second.
Yeah. Okay. Let him go. Let him continue.
He made the point that the problem with his robot that he didn't have enough of a loop, a large enough loop in order for it to be fully conscious. But the robot exhibits behaviors that are very similar to the way children learn, and he basically said that every time that the loop would run around, it would have to restart again, because he didn't have enough. Some kind of storage, but it wasn't digital. It's not that the machine was not digital. And the other thing that he pointed out, and I thought that was great. He posted a note on the SETI League. I don't know if you guys know who the SETI League are.
Yes.
He claimed that he had a quantum robot with a CCD camera staring at a picture of Earth as a CE5 contact experiment with aliens in outer space. Okay. yeah, I thought you get it.
No, it's possible. I'm not.
I mean, it was quantum entanglement experiment. Basically, he's talking about telepathy here, machine telepathy. Well, one of the things that his machines exhibit is psi sensitivity. He can modify the behavior on the floor by thinking at them. And
but if he's using Josephson junctions, there's a macro quantum wave function there. So if that's the core to what he's doing, it might make some physics sense, but yeah, I'd have to, I don't know, I'm just guessing.
Anyway, that was my whole point, and I just wanted to share that with you guys because the information's out there somewhere. I don't know exactly where it is, because most of it has disappeared. You know, the internet's so broken
There
now.
was a Ron Blue who used to send me emails, and I don't know if it's the same guy.
Ron Blue, Dr. Ron Blue.
Yeah, but I never paid much attention to them for some reason, but I don't remember. It may not have been the same guy because he never mentioned these robots. I would have paid attention if he mentioned the robots.
Was he talking about quantum mechanics and quantum, quantum consciousness?
I don't know.
Because that was his whole deal, man.
This is like 20 years ago, so I don't really.
Yeah, it was about 20 years ago.
No, it was a different. I think it was a different guy. It doesn't sound like this guy. Just the same name.
You know, I'd like to thank everybody for today's conference. Jack, I think today went so well. I'm just pleased as punch. I'm just amazing presentations, amazing ideas, wonderful discussion.
So when will you have this up on the web?
Uh,
I should have this uploaded tonight.
Really? Oh,
Yeah,
what about
yeah.
this? What about
It never sleeps.
wait. But what about the second day? What about yesterday? Because you haven't.
Oh,
done
no,
that.
I uploaded that. You know, I just didn't send you a link yet, but that's that. Yeah, I put that up last night.
Okay, but please send the link. Okay.
Okay. Yep. And
Okay.
yeah, my hope with these is, again, I'm putting the conferences up on the Alt Propulsion site, and then I'll do breakouts for individual speeches, and I'll put those up on the interviews channel. And that way my audience won't get upset with me. So.
Oh, good. Okay, that's a good idea.
Yeah.
Excellent.
Yeah. I'll just break them out. I'll split them up.
Yeah. Oh, perfect. Okay. All right. So that's it. Who's still here? God, some people stayed. David, Cheb, Frank. Let me see if she's still here.
Yeah.
Still
Well,
on?
again, wonderful conference, wonderful presentations,
Wait,
wonderful
now, is
discussion.
that Mark? Who's Marco? Is that Marco Gauss? Who's
think so.
Marco? Is that Marco Gauss?
I think he spoke earlier and he had an Italian accent. I think it's one of your.
Yeah,
colleagues.
it's me.
Oh, that's you. Okay.
Yeah,
Right.
I'm from the group of Italy with Carbuno Vedruccio and Gaetano Battaglini.
Yes. Wait a minute. Did I meet you? Wait, you're not in Firenze, are you? No. Are you in?
No, I'm actually in Torino.
Yeah. Oh, no, yeah. Okay. No, okay. No, there's a different Marco who I know in Florence, but no, you're not him. Okay.
You know Marco Pettini, maybe?
You know. Oh, all right. Well, nice meeting you. All right. So is that it? Are we going to sign off now, or anybody else got anything earth-shaking they want to say?
I don't know. I had a great time.
Yeah.
It was
okay.
it was really
Learned a lot of
good.
stuff.
It was really interesting. Really
Yeah.
great.
Yeah, today was wonderful. And I think tomorrow we have wonderful people lined up as well. So Jack, thank you. Thank you for putting this event together. It's a privilege to be able to
Thank you.
moderate.
Jim, is there any way to see people's slides? Is there any way to look? Will we be
Yeah,
able to look back at people's slides and
When you
actually
look
see-
on the video, you could freeze it. You just pause it.
Oh, okay.
Yeah,
Yeah,
go
yeah,
on
yeah.
the video.
You just go on the channel. You just hit the
Okay,
pause,
excellent.
and you do
Yeah.
a screen capture. Screen capture, and you have it.
Okay. Well, why don't I close things down again? Thank you.
Okay.
Thank you so much.
Right.
It's
Yeah.
truly
All
an
right.
honor.
Ciao. Okay. Bye-bye.
Bye.
Bye, everybody.
Bye.
Talk to you later, Jack.